Currently, an extraordinary object from beyond our solar system is hurtling toward us at an astonishing speed, 61 kilometers per second. Yet curiously, the only voices raising alarms or sharing insights about this cosmic visitor belong to amateur astronomers and a single outspoken professor from Harvard. Strangely enough, NASA remains eerily silent on the matter, offering no official commentary, while the European Space Agency has only issued a handful of sparse technical blog posts, providing little more than background details without any sense of urgency or spectacle. Meanwhile, behind closed doors, hundreds of defense officials have convened at the Marine Corps base in Quantico for a secretive meeting that no one will explain. Could this coincidence be just that? Coincidence? Or does it hint at something more profound? What makes this particular object, designated as 3I Atlas, distinct from countless other cosmic wanderers is its apparent intent and trajectory. It is threading through our planetary neighborhood as if it possesses a knowledge of where it's headed, visiting Mars on October 3rd, then Venus in November, Earth in December, and Jupiter next spring. Such a precise multi-planet journey along a single trajectory suggests deliberate navigation. Strangely, during this period, our planet's institutions have seemingly forgotten how to hold a proper press conference. No dramatic announcements, no official explanations, just silence, and the story gets even more intriguing. As this interstellar object approaches its perihelion, its closest point to the Sun, Earth's telescopes suddenly go blind. Solar glare becomes so intense that observation becomes impossible for weeks, leaving Mars orbiters as our sole eyes on the visitor. Stay with us until the end, because what we uncover in December, when Earth's telescopes can finally reacquire the object, might depend entirely on what we're willing to question now. NASA's silence is unlikely to be accidental. Understanding the reasons behind it is essential. So let's delve deeper into this paradox. Part 1. The paradox. Right now, as the object known as 3I Atlas slips past Mars, NASA's silence continues to be conspicuous. Take a moment to reflect on what this silence might imply. We have in this moment a visitor from another star system, only the third confirmed interstellar object in human history, making its closest approach to Mars in just a matter of days. This is not some distant celestial curiosity passing billions of miles away, unnoticed and insignificant. This is an object that originated in an alien solar system, journeyed through the vast, dark expanse of interstellar space for potentially millions of years, and is now threading its way through our neighborhood with apparent purpose. And yet, if you search for live media coverage, press conferences, breathless announcements, or even the usual media frenzy, you will find almost nothing. Instead, what exists are sparse updates on official websites, a few technical blog posts, some observations quietly uploaded to archives from the Hubble Space Telescope, and a preprint from the James Webb Space Telescope that was published with minimal fanfare on the preprint server, Archive. Even the European Space Agency, which operates Mars orbiters like Mars Express and the ExoMars Trace Gas Orbiter, has issued routine questions about the object, as if it were just another routine satellite passing overhead. This stark contrast forms the paradox: maximum celestial drama, minimal institutional response. The breadcrumbs, those small clues and data points, do exist, but they require knowing where to look. On July 2nd, 2025, the Minor Planet Center officially designated this object as 3I Atlas, a name that tells us everything. The 3I indicates it's only the third confirmed interstellar object in our recorded history, following the 2017 discovery of Oumuamua, 1I, and the 2019 detection of Borisov, 2I. The Chile-based Atlas survey, first spotted the object on July 1st, already on a hyperbolic trajectory that screams not from around here. Once its orbit was calculated, it became clear this object was coming from beyond our solar system, traveling at roughly 61 kilometers per second relative to the Sun, following a path that could never be bound by our star's gravity alone. What makes this object even more remarkable is its trajectory. It is threading through our planetary neighborhood with a precision and purpose that resemble a guided mission. It is scheduled to approach Mars on October 3rd, then head toward Venus in November, and finally pass Earth in December, with Jupiter in the spring. These sequential planetary encounters are not random. They suggest a deliberate, possibly engineered path. And during all this, official agencies have failed to hold a proper press conference. No dramatic countdowns, no live broadcasts, no coordinated media efforts, just quiet technical updates. The story only deepens as we examine the chemistry and physical characteristics gleaned from observations. The James Webb Space Telescope in late August detected that the coma surrounding 3I Atlas is dominated by carbon dioxide, a highly unusual finding. The object is now traversing space at an astonishing speed, approximately 61 kilometers per second relative to the Sun, and follows a trajectory that could never be completed solely by the gravitational pull of our star. Its journey clearly indicates it originated from somewhere beyond our solar system, arriving from the depths of interstellar space. On August the 7th, the Hubble Space Telescope provided a crucial update. Astronomers have estimated the size of its nucleus, placing an upper limit of around 5.6 kilometers in diameter, possibly as small as a few hundred meters, while the nucleus itself remains unresolved directly, hidden within a luminous cloud of gas and dust known as a coma. The measurement of its size is far from trivial. In planetary science, size is directly linked to mass. Knowing the mass allows us to estimate how much force the object can exert on itself or be affected by, without relying solely on outgassing jets or other non-gravitational influences. Then, on August the 25th, the team operating the James Webb Space Telescope released a preprint, an early version of their findings, marking a turning point in understanding this interstellar visitor's chemical makeup. We will delve into those details later, but for now it's important to grasp that the coma surrounding 3I Atlas is overwhelmingly dominated by carbon dioxide. The ratio of carbon dioxide to water vapor in the coma is approximately 8:1. A figure that ranks among the highest ever recorded in any comet within our solar system. Such a composition is highly unusual. It signals that this object isn't following the typical chemical profile we expect from comets formed in our local stellar neighborhood. Instead, it hints at an exotic, perhaps even alien origin. As September transitions into October, the European Space Agency announced that their Mars orbiters, Mars Express and the ExoMars Trace Gas Orbiter, would undertake an observation campaign targeting the approaching object from October the 1st through the 7th. The closest approach to Mars is scheduled for October the 3rd, at a distance of roughly 30 million kilometers. While that distance might seem vast, about 80 times the space between Earth and the Moon in terms of kilometers, in the context of interstellar objects making a flyby of a planet, this is remarkably close. It's akin to threading a cosmic needle, offering a rare opportunity for detailed observation. However, then comes what is often called a blackout, but not in the sense of a cover-up or conspiracy. Instead, it's a blackout dictated by the geometry of the solar system and the physics of observation. Around the time of perihelion, the point in its orbit closest to the Sun, around October the 30th at approximately Odin-Tochka-Chatiri astronomical units from the Sun, Earth's line of sight to the object is obstructed. From our vantage point, the object passes too close to the Sun in the sky, making direct observations either unsafe or impossible. Telescopes on Earth cannot safely point toward the sun's direction without risking damage or being overwhelmed by solar glare. Space-based observatories like Hubble and JWST face similar restrictions. They cannot look too close to the sun either. Consequently, as the object approaches perihelion during this critical phase, we effectively go blind, missing the most dynamic part of its journey. We will not regain a clear view until early December, by which time the object will already be outbound, retreating from the sun and cooling down. The current situation involves early October observations from Mars, a subsequent month-long observational gap on Earth, and a return to viewing in December. Throughout this entire process, the official communications from the major space agencies have been notably technical, restrained, and nearly bureaucratic in tone. It's as if the language used aims to maintain scientific caution rather than generate excitement. No dramatic press conferences, no countdowns, no hype videos. This may simply reflect how science operates. Caution is a virtue in planetary science. No one wants to repeat the mistake made with Tabby's star, where premature claims about an alien megastructure turned out to be errors or misinterpretations. Institutional culture emphasizes multiple observations over time, peer review and cross-checking against models, processes that require patience and time. Yet this cautious approach introduces a palpable tension. There exists a growing gap between what the institutions are officially communicating, dry, measured updates, and the more vocal, often sensational voices of amateurs, small observatories, and a handful of high-profile scientists who are raising questions, pointing out peculiarities, and sometimes suggesting extraordinary possibilities. This divergence in narratives fuels a sense that something more is happening behind the scenes, an uncertainty that many observers are eager to interpret, and in the absence of official explanations, speculation begins to fill the void. While official channels like NASA tend to release sanitized, carefully curated updates through their blogs, designed to keep the narrative controlled, independent observers equipped with advanced telescopes and the global network of Las Cumbres observatories are actively sharing raw, unfiltered images that reveal peculiar tail structures and other anomalies. These raw images, often posted by dedicated amateur astronomers or small observatories, depict features that seem unusual, potentially indicating activity or morphology inconsistent with routine cometary behavior. Meanwhile, the European Space Agency, which maintains a frequently updated FAQ page to address common questions about their missions and observations, continues its steady, methodical dissemination of information. Yet, among the scientific community and the enthusiast circles, one prominent figure stands out. R.V. Loeb, yes, that R.V. Loeb, the Harvard astrophysicist renowned for his outspoken assertions that objects like Oumuamua or Muir could potentially be artificial in origin. Loeb is openly floating the provocative idea that the interstellar object known as 3I Atlas might warrant closer scrutiny precisely because of its peculiar trajectory and characteristics. His suggestion is not based on evidence of artificiality, but on the premise that extraordinary objects merit extraordinary attention, especially when the official silence appears conspicuous. The reality is, the silence from the major institutions isn't absolute, it's selective. This selectivity creates a vacuum, an information gap, that inevitably gets filled. In this space, speculation flourishes, pattern recognition becomes rampant, with individuals connecting dots that may or may not belong together, constructing narratives that can be compelling but are often speculative at best. This vacuum is further complicated by the mysterious presence of Quantico, a detail we will explore more thoroughly later but which already plays a significant role in shaping the optics and the narrative web surrounding this interstellar visitor. In late September, as 3I Atlas approaches Mars, the story takes a dramatic turn. News surfaces that U.S. defense leadership has been summoned to Marine Corps Base Quantico for an unexpectedly large, short-notice gathering. The official story remains deliberately vague. The purpose of the meeting is framed as routine or strategic discussions, with the media describing it as rare, abrupt, and urgent. The White House downplays the event, claiming it's just standard protocol, yet the timing of this gathering raises eyebrows. Why now? Why so suddenly? Is there any verified link between Quantico and the interstellar object? So far, publicly, there's zero concrete evidence connecting these two events. No leaked documents, no official statements, no classified briefings, nothing that confirms a direct relationship, and yet the coincidence in timing feeds the fertile ground of conspiracy theories. The idea that these events are intertwined is a favorite narrative trope for those seeking patterns in chaos, feeding the suspicion that something significant is unfolding behind the scenes. The core thesis of this unfolding story isn't about explaining what a comet is, because most of us already understand that. Instead, it's about examining what exists in the gaps, the spaces between official data releases and the public's perception, the observational blind spots created by geometry and physics, and the critical moments when visibility vanishes precisely when the object might be most active or revealing. This narrative revolves around who fills those gaps when official channels remain silent, whether it's amateur astronomers, science communicators, or even contrarians, and what the consequences are when speculation takes center stage. We will dissect the deluge of information, carefully differentiating peer-reviewed data from preprint hypotheses, from outright rumors. We'll classify what is confirmed, what is plausible, what is exotic, and what is outright bonkers. Every date, measurement, and source will be rigorously documented, ensuring transparency and accountability. But before diving into the intricacies, it's essential to establish what we already know, what concrete facts are available, and where the cracks in the public record lie. These cracks matter because they shape the narrative and influence how we interpret the data, especially during moments of silence and uncertainty. We'll explore the verifiable facts surrounding 3I Atlas, highlighting the gaps and explaining why understanding these gaps is vital. Part 2. What we do know and the cracks in the public record. Let's begin with the undeniable facts, those numbers, observations, and data points that have been independently verified and are accessible across multiple databases. The first discovery and official certification came through the Atlas survey in Chile, operated by the Asteroid Terrestrial Impact Last Alert System, an automated sky survey designed specifically to detect near-Earth objects before they pose any threat. On July 1, 2025, this system flagged an unusual fast-moving point of light that moved across the sky in a way unlike most natural objects. This initial alert set the stage for further follow-up and analysis. From there, the process of confirmation unfolded swiftly. The Minor Planet Center, the global authority responsible for collecting and certifying asteroid and comet observations, rapidly processed the data. Within 24 hours, they confirmed that this object was on a hyperbolic trajectory. Within a mere 24 hours of its discovery, the Minor Planet Center, recognized as the definitive international authority for cataloging asteroid and comet observations, immediately took action. They processed the orbital calculations and arrived at a conclusion that confirmed what many had begun to suspect. This object was on a hyperbolic trajectory, a path that defied the bound orbits typical of objects born within our solar system. The key indicator was the orbit's eccentricity, a value greater than 1, a precise mathematical signifier that it was not gravitationally tethered to the Sun. Instead, it had arrived from beyond our stellar neighborhood, from interstellar space itself. Due to this, it was assigned the official designation of 3I Atlas, with the formal cataloging name C/2025N1. The letter C here is significant. It denotes that the object exhibits cometary activity, meaning it sports a surrounding cloud of gas and dust, a coma, and is actively outgassing, releasing material into space, indicating it is more than just a dormant rock drifting through the void. At the moment of its discovery, this interstellar visitor was hurtling inward at approximately 61 kilometers per second relative to the Sun. To put this into perspective, the fastest spacecraft ever launched by humanity, the Parker Solar Probe, reaches speeds of about 192 kilometers per second at perihelion, the closest approach to the Sun. However, the Parker is aided by gravitational assists and is falling directly toward the Sun, whereas 3I Atlas is carrying its high velocity from the depths of interstellar space, gradually decelerating as it climbs into the Sun's gravitational influence. This journey's geometry and timeline paint a compelling narrative. The object will make its closest approach to Mars on October 3rd of 2025, passing about 30 million kilometers away. To give a sense of scale, that distance is roughly 0.19 astronomical units, with one astronomical unit being about 150 million kilometers, the average distance from Earth to the Sun. In astronomical terms, 0.19 AU is exceedingly close enough for Mars-based instruments to obtain a solid, detailed observation, yet far enough to avoid any collision risk or threat of impact. Following this, the object continues its inward voyage toward perihelion, its closest point to the Sun, on October 30th, 2025, at roughly 1.4 astronomical units from the Sun. This position places it well within Mars's orbit, but nowhere near Earth's vicinity. Its closest approach to Earth will occur much later in its course, at a distance of about 1.8 astronomical units, far enough away that there is absolutely no danger to our planet. It's crucial to emphasize this because the last thing anyone needs now is a panic rooted in false fears of impact or catastrophe. This is not an impact scenario. It's a rare, extraordinary observational window, a scientific opportunity. The first significant data came from the Hubble Space Telescope on August 7th. Although Hubble couldn't directly resolve the nucleus, the dense core of the comet, due to its small size and the object's distance, it provided an upper limit estimate on the nucleus's size. By analyzing the brightness of the surrounding coma, the glowing envelope of gas and dust, the scientists could infer the amount of solid material necessary to produce such activity. The resulting estimate suggested that the nucleus is likely no larger than about 5.6 kilometers across, but potentially as small as a few hundred meters. This range has enormous implications. A 5-kilometer nucleus would be a sizable comet with significant mass and gravitational self-binding, capable of withstanding various forces. Conversely, a nucleus only a few hundred meters in size would resemble a fragile rubble pile, barely held together, vulnerable to tidal disruption or rotational breakup, while the coma, an ethereal glow of reflected sunlight and self-emitted fluorescence, was vividly observable and beautiful. The nucleus itself remained unresolved, hidden within a fuzzy cloud. It presented as a tiny dark seed shrouded by a luminous haze. Meanwhile, the James Webb Space Telescope, JWST, provided critical insights into the comet's chemistry, marking the beginning of a series of discoveries that would make the object's nature even more intriguing. The chemical composition revealed by JWST was startling, hinting at phenomena that defied expectations and opened new questions about the object's origins and characteristics. In late August, our infrared powerhouse, the James Webb Space Telescope, pointed its advanced spectroscopic instruments directly at the interstellar object known as 3I Atlas. The data collected during this crucial observation was subsequently published as a preprint on the arXiv repository, authored by members of the mission team. The fact that it comes from the scientists directly involved lends it considerable weight and credibility, even though it has not yet undergone formal peer review. What do these findings reveal? The spectroscopic analysis shows that the comet's coma is overwhelmingly dominated by carbon dioxide. Accompanying this main component are traces of water, carbon monoxide, and carbonyl sulfide. The ratio of carbon dioxide to water is approximately 8:1. Plus or minus 1, meaning there are roughly 8 parts of carbon dioxide for every single part of water, an extremely unusual chemical signature in the context of cometary bodies. To put this into perspective, most comets within our solar system are water-rich. Water ice is their primary volatile component, with carbon dioxide and carbon monoxide present only in secondary quantities. In stark contrast, 3I Atlas defies this norm. Its composition resembles more of a fizzy soda than a steaming brew, more dry ice than water ice. This kind of chemical makeup flips the traditional script of cometary structure, suggesting an environment and formation process that differs markedly from typical solar system comets. Meanwhile, the European Space Agency adds another valuable layer to our observational picture. Currently orbiting Mars are 2 spacecraft, Mars Express and the ExoMars Trace Gas Orbiter. The agency has announced an observation campaign scheduled from October 1st to 7th, with peak data collection aligned with the comet's closest approach to the red planet on October 3rd. Both orbiters are equipped with spectroscopic instruments, such as NOMAD and the Atmospheric Chemistry Suite, ACS, on the Trace Gas Orbiter, and SPICAM and OMEGA on Mars Express, designed specifically to analyze atmospheric gases. These instruments can be directed toward 3I Atlas during this window to capture detailed, time series spectra of the comet's coma. By doing so, scientists can monitor how the gas composition evolves as the object approaches the Sun, providing real-time insights into its activity. This period represents our most promising observational opportunity precisely because of what comes next. The challenge, however, is the so-called observability gap, an inevitable interval when Earth-based telescopes will be unable to observe the comet. As 3I Atlas nears perihelion on October 30th, it will pass extremely close to the Sun from our vantage point. This proximity results in a phenomenon known as solar conjunction, during which the comet appears too close to the Sun's glare for telescopes to safely point in that direction. When they do attempt to observe, the signals are overwhelmed by scattered sunlight, rendering detailed spectroscopy impossible. Space-based solar observatories like SOHO, Solar and Heliospheric Observatory, and STEREO, Solar Terrestrial Relations Observatory, might detect some broad dust dynamics during this period, but neither is optimized for detailed small comet spectroscopy. Consequently, we will be effectively blind to the object during its most active phase, precisely when internal ice is being baked and outgassing likely reaches its peak. The first opportunity to regain a clear view won't come until early December, by which time the comet will already be on its outbound journey, cooling down after perihelion. This creates a narrative and data gap, an interval where critical changes may occur but remain unobserved. Now, beyond the technical and observational challenges, certain narrative cracks become apparent. The tone and cadence of official updates from institutions like NASA are notably restrained. Their reports on 3I Atlas resemble technical blog entries, dry, factual, aimed at an audience familiar with scientific terminology, with no live press briefings, countdowns, or hype videos. The language is straightforward and informational, not theatrical. This contrasts sharply with how agencies have historically celebrated moments like the Mars Perseverance landing, the DART asteroid impact, or the James Webb's first light images, which were treated as media events with extensive coverage and dramatization. In these terms, 3I Atlas is receiving a much more subdued treatment. It's being discussed through official channels primarily via written blog posts and technical updates, rather than as a spectacle. This restrained approach raises questions about the narrative strategy, whether it stems from cautious scientific prudence or a broader institutional reticence about drawing attention to a potentially extraordinary object. Certainly, here's a richly expanded, cohesive rephrasing of that segment, emphasizing clarity, flow, and detail. One of the most striking aspects of the current situation is how fragmented the available data sets are. If someone truly wants to grasp the full scope of what's unfolding with 3i Atlas, they must engage in a complex process of piecing together information from multiple sources. There is no single centralized hub, no dedicated, continuously updated landing page or dashboard that consolidates all the relevant observations and findings. Instead, enthusiasts and researchers must sift through a patchwork of different platforms. The circulars issued by the Minor Planet Center, the output files and ephemeris calculations from JPL Horizons, NASA's official pages for Hubble observations, preprint servers like RXIV, and ESA's dedicated pages for their Mars missions. This fragmentation inherently complicates efforts for casual observers or even dedicated scientists attempting to keep track of developments. Because information is scattered across various sites and reports, each requiring effort to locate and interpret, the task of assembling a comprehensive picture becomes daunting. The more effort that's required to access the data, the fewer people tend to do so. As a result, the perception of silence, an impression that little to nothing is being communicated or that key information is being deliberately withheld, begins to grow. This perception, whether justified or not, feeds into a narrative of mystery and secrecy, even if no overt attempt at concealment exists. The third major factor influencing this narrative landscape is what can be called the media asymmetry. Mainstream scientific outlets, publications like Nature, Scientific American, or science-focused websites such as space.com, have reported on 3i Atlas, but they have done so with cautious restraint. Their headlines tend to be measured and cautious, emphasizing the tentative preliminary nature of the observations. New interstellar visitor detected, or Mars orbiters to observe unusual comet. They avoid sensationalism, sticking to the facts as they are understood at this stage. Meanwhile, the more speculative interpretations flourish on social media and informal channels. Pervasive questions emerge. Is this an alien probe? Why is NASA seemingly hiding or downplaying the object? Why are there no loud announcements or grand press conferences? The truth is, it's not necessarily that there are more of these sensational claims, they are fewer in number, but that they are far more shareable and emotionally engaging. Sensational stories capture attention and spread rapidly, often outpacing the more cautious, measured reporting. This disparity in narrative styles matters because the combination of low-drama official communication, press releases that are technical and dry, and the coincidental timing of high-impact events like a close planetary flyby can lead to a widespread perception of silence. Even when institutions are actively gathering data and conducting analysis, the lack of immediate spectacle or grand announcements can be misconstrued as concealment or suppression. The absence of dramatic visuals or announcements in this context gets misread as an intentional cover-up, even when it might simply reflect an institutional culture prioritizing scientific rigor and caution over sensationality. Yet beneath these optics lie authentic scientific mysteries and anomalies. The composition of 3i Atlas, for instance, exhibits peculiarities that challenge our expectations, quirks that may be explained by natural processes or intriguingly suggest something more exotic. The behavior of the object also defies easy categorization. It's important to clarify that weird in this context doesn't automatically imply artificial origin. Rather, it indicates that our current understanding of such objects is incomplete. These anomalies highlight the essential role of science to investigate phenomena that do not fit neatly into existing models and to seek explanations for what we observe. Now, let's delve into these anomalies, which are supported by data, either peer-reviewed or at least pre-printed, making them compelling reasons to pay close attention to 3I Atlas. These anomalies in both the object's chemistry and its behavior are what elevate its significance beyond mere curiosity. Would you like me to continue with the detailed analysis of these anomalies? What are the potential explanations for the peculiar observations of this interstellar object? One plausible scenario is that it originated in a region of its parent star's protoplanetary disk where carbon dioxide ice was inherently more stable than water ice. Different stars, after all, have varying levels of luminosity and radiation environments, which affect where their snow lines, the boundaries where specific volatiles condense, are located. In other words, the volatile composition of a comet can be heavily influenced by the conditions of its formation environment. This leads to the possibility that 3I Atlas formed in a much colder, more carbon-rich zone than the typical comet factories in our solar system. If that's true, then its composition would be genuinely alien, not merely in its origin but in its very makeup, offering a direct snapshot of a different stellar chemistry. Such an object would serve as a tangible record of a foreign stellar environment, a chemical fingerprint that challenges our conventional understanding of comet formation within our own solar neighborhood. Alternatively, another explanation hinges on the internal structure of the comet. In this model, water exists within the nucleus but remains locked beneath an insulating layer of carbon dioxide and dust. Since CO2 sublimates, turns directly from solid to gas, at much lower temperatures than water ice, the outer layers of the comet could begin venting CO2 as it approaches the sun, while the water ice beneath remains frozen for longer. This process creates a sort of fizz before the steam. We're witnessing the release of carbon dioxide gas, which gives the impression of activity, even though the more volatile water remains dormant deep inside. If this scenario holds, we might expect the water signal, the amount of water vapor in the outgassing, to increase after perihelion, once the solar heating penetrates the deeper layers and unlocks the buried H2O. Observing a rise in water activity post-perihelion would lend support to this layered insulation model. A third, more speculative explanation involves the heterogeneity of the nucleus's surface. In this view, the comet's surface isn't uniform but patchy, with some regions rich in water ice and others dominated by carbon dioxide. Currently, during the flyby near Mars and as the object approaches perihelion, the CO2-rich side might be facing the sun, actively venting gases. As the nucleus rotates, something we know it does evidenced by the variations in brightness, different regions are exposed to solar heating. This rotational exposure would cause episodic outgassing events, with some areas releasing more gas at different times, leading to irregular patterns of activity. Such a patchy, rotating surface could account not only for the high CO2 levels observed, but also for the irregular light curves reported by amateur astronomers and observatories. These brightness fluctuations, characterized by flickers and pulsing activity, are well documented and reminiscent of what has been observed in other comets like Hartley 2 and Tempel 1, which also exhibit episodic jets and non-smooth brightening. This erratic behavior suggests a nucleus with heterogeneous volatile distribution, where localized active regions turn on and off as different patches face the sun. An intriguing hypothesis within this framework is that the nucleus might have a thin crust of dust that temporarily traps pockets of gas underneath. As solar heating causes sublimation, pressure could build up beneath this crust until it cracks, leading to sudden outbursts of gas and dust. After venting, the crust could reseal, only to break again as internal pressure accumulates anew. This thermal wave model, where heat gradually penetrates the interior, could produce the observed episodic jets and explain why low-temperature volatiles like CO2 dominate early in the approach. Such a process is testable. If during the perihelion passage observations reveal sudden spikes in gas emissions or transient jets, it would support the idea of subsurface pockets of volatile-rich material suddenly venting. Adding to the puzzle, the comet's surface might appear to plume or develop unusual tail structures. Some images suggest a tail or plume extending toward the sun, which appears counterintuitive since solar radiation pressure and the solar wind typically push dust and gas away from the sun. However, this could be a visual illusion known as an anti-tail, where dust particles along the orbit are aligned in such a way that, from our perspective, they seem to point sunward. This phenomenon has been observed in other comets, such as Comet Aaron-Rowland in 1957. In such cases, the apparent sunward tail is not a propulsion mechanism but an optical illusion resulting from the geometry of the dust trail viewed edge-on. Overall, these explanations highlight the complexity and diversity of possible mechanisms behind the observed phenomena. Whether the cause is an inherently alien chemistry, layered insulations within a heterogeneous nucleus, episodic outbursts from subsurface pockets, or geometric illusions, each hypothesis offers a testable prediction. The true nature of this interstellar visitor remains a captivating mystery, inviting us to refine our models and expand our understanding of the diverse processes shaping objects from beyond our solar system. Some amateur astronomers have captured images that reveal what appears to be a tail or plume stretching toward the sun, rather than away from it. At first glance, this seems counterintuitive, doesn't it? Conventional physics dictates that solar radiation pressure and the solar wind should push dust and gas particles away from the sun, which is exactly what they do in most cases. However, there's a well-documented optical illusion known as an anti-tail, which can create the appearance of a tail pointing sunward, even though it actually follows the comet's orbital trajectory. This phenomenon occurs when our line of sight aligns in just the right way to observe the dust trail from the edge-on perspective, making it look as if the tail is headed toward the sun. Historically, this has been observed in other comets. For example, Comet Aaron-Darrell in 1957 famously exhibited an anti-tail, highlighting how geometry, not propulsion, is usually responsible for such visual effects. In the case of the comet in question, the sunward plume is most likely a matter of observational geometry rather than any exotic or unknown propulsion mechanism. Nevertheless, such an appearance sparks curiosity and lends an aura of the extraordinary to what might simply be a perspective-based illusion. The visual impression of a tail pointing toward the sun naturally attracts attention and fuels speculation. Exotic-looking features tend to do that. One significant issue that remains unresolved is the uncertainty surrounding the size of this interstellar object, and surprisingly, this uncertainty is more critical than it might initially seem. The Hubble Space Telescope provides an upper limit estimate of about 5.6 kilometers for the nucleus's diameter. But this figure hinges on assumptions about the surface's reflectivity, its albedo, and on how much dust and gas the nucleus is currently producing. If the surface is darker than the assumptions suggest, the object could be larger since darker surfaces absorb more sunlight and therefore appear dimmer. Conversely, if the nucleus is more reflective, it could be smaller. Similarly, if the object is generating more dust and gas than expected, the mass estimate derived from brightness measurements would decrease, complicating our understanding of its true size and mass. Until we acquire more precise astrometric data, measurements of the object's position and motion, and can accurately gauge the non-gravitational accelerations caused by outgassing jets, our ability to determine its mass remains limited. These jets act like miniature thrusters, subtly altering the orbit, and tiny variations in the orbit could reveal much about the mass and internal structure. Without accurate mass estimates, fully understanding the dynamics and the true nature of this interstellar visitor remains elusive. To understand how this compares, it's useful to contrast this object with 2I/Borisov, the first confirmed interstellar comet, discovered in 1997 and extensively observed during its passage through our solar system. Borisov was notably rich in carbon monoxide, an unusual feature. Yet its overall composition aligned broadly with typical solar system comets. Water was detected as well as carbon dioxide, and the ratios of these volatiles fell within the normal range observed in comets originating from our Oort cloud. Borisov felt familiar, like a comet from a different star's distant cloud, yet still within the known parameters of cometary behavior. In stark contrast, this interstellar object, often referred to as 3I Atlas, exhibits a remarkably different profile. Its extreme dominance of carbon dioxide, episodic outgassing activity, and a high abundance of carbonyl sulfide push the boundaries of what we usually consider normal for comets. Why might interstellar objects be so different? The answer lies in their origins. They formed around stars in diverse chemical environments, possibly long before our solar system even existed, and in regions with varying levels of radiation, stellar winds, and supernova enrichment. Interstellar material, the gas and dust that drifts between stars, does not have a uniform composition. Different regions of the galaxy are enriched to varying degrees by supernova explosions, stellar winds, and cosmic radiation. A protostellar disk that forms in a region enriched with carbon from previous stellar generations might produce comets with significantly higher carbon dioxide content than those formed in more pristine, colder regions farther from the star. Essentially, what we are seeing is like a chemical fingerprint, written in ice, of an alien stellar chemistry, a direct imprint of a star system's unique history. Building on this, there's a further speculative hypothesis to consider. What if the nucleus contains internal pockets of volatile rich material, like bubbles or cavities that have accumulated beneath the surface? Such pockets, if existent, could dramatically influence the comet's behavior as it approaches the Sun. Variations in internal composition, structural heterogeneities, or trapped volatile reservoirs might periodically release gas in sudden bursts, leading to episodic outgassing events. This internal heterogeneity could explain irregularities in outgassing patterns, brightness variations, and perhaps even the formation of transient features like jets or plumes. This idea opens intriguing possibilities. Pockets of volatile rich material could be. As the surface of this celestial body begins to warm and undergo sublimation, it exposes previously hidden pockets of volatile materials beneath the crust. When these pockets are suddenly revealed, they can produce localized outbursts of gas that weren't directly connected to the surface layers before. Essentially, the nucleus appears to breathe, but this isn't just a matter of simple composition. Instead, it reflects a complex internal structure, one that is heterogeneous with varying layers and pockets of volatiles distributed unevenly throughout. This dynamic process can be rigorously tested through time series spectroscopy. If the orbiting spacecraft around Mars detect abrupt increases in the emission of carbon dioxide or observe the emergence of new molecular species during specific intervals, these would serve as compelling evidence for such pocket outbursts, internal regions suddenly releasing their stored gases. An additional noteworthy detail involves the presence of carbonyl sulfide, commonly abbreviated as OCS. Though this compound is a trace species, a minor component within the comet's outgassing material, its detection by the James Webb Space Telescope carries significance. In the context of our solar system, Carbonyl sulfide is relatively rare among comets, but it's not entirely unheard of. Its presence points towards sulfur chemistry within the nucleus, hinting at the chemical environment present during the comet's formation. The detection of sulfur-bearing molecules like OCS, alongside potential precursors such as hydrogen sulfide or sulfur dioxide, suggests that the formation environment of this object involved specific conditions that favored sulfur chemistry. If 3I Atlas is enriched in these sulfur compounds, that offers valuable clues about the composition of its original protoplanetary disk and the chemical pathways that were active when it was formed, potentially revealing an alien chemistry that deviates from typical solar system comets. In summary, 3I Atlas presents an intriguing combination of traits. It is compositionally unusual, exhibiting a high degree of erratic behavior, and its visual appearance can be deceiving. Most likely it is a natural comet, but one that pushes the boundaries of our current understanding and models. This is evident not only in its chemical makeup, but also in its unusual trajectory, orbital geometry, and the uncanny sense that its path through the solar system is almost too convenient, almost as if it were purposefully planned or engineered. This raises a provocative question that many hesitate to voice, yet one that cannot be ignored. Could there be any possibility that this object's journey was in some way deliberate? This question brings us to the next phase. Part 4. Trajectory and Intent, where we delve into the so-called alignment hypothesis. Here the focus sharpens on the orbit itself, because this is where the speculation becomes more intense and where we must exercise extreme caution in interpretation. The orbit of 3I Atlas is retrograde, meaning it travels in the opposite direction to the orbit of most planets, including Earth, around the Sun. Such retrograde motion is typical for interstellar visitors, as they can enter our solar system from any angle and in any orientation. However, what makes 3I Atlas particularly intriguing is its orbital inclination, which is only about 5 degrees from the ecliptic plane, the flat disc-shaped region in which Earth and most other planets orbit the Sun. To put it simply, this inclination is nearly coplanar. Imagine a car merging onto a highway. Most vehicles follow the lane quite closely, aligned with the flow of traffic just slightly off to the side. Now picture this car merging at almost a perfect angle, nearly parallel to the main flow but moving in the opposite direction. That's the visual analogy for its orbital inclination. Nearly aligned with the planetary plane, yet moving counter to the general direction of planetary orbits. Why does this matter? Because in the broader context of interstellar objects, most are expected to arrive at steeper angles, coming in from directions that do not align with the ecliptic plane at all. Space, after all, is a three-dimensional environment, and the majority of objects traversing the galaxy should encounter the solar system from a variety of angles and inclinations, not just nearly coplanar with the planetary disk. If you think about it like a game of pool, where balls are randomly struck from various angles, most will hit the felt at high or low angles, not skimming along the surface. Yet 3I Atlas appears to be skimming along the felt, moving almost along the plane of the planetary orbits. Of course, before jumping to conclusions, it's important to consider the role of observational bias. Our sky surveys, which are the primary means of discovering such objects, tend to focus along the ecliptic because that's where most of the interesting solar system objects, asteroids, comets, near-Earth objects, reside. Consequently, our detection methods are inherently biased toward objects that travel close to this plane. This is akin to searching for your lost keys under the streetlight because that's where the light is. The keys might be elsewhere, but in our quest to uncover cosmic visitors, we tend to focus our telescopes where the action appears to be, namely along the ecliptic plane, the flat disk-like region where most of the solar system's planets and smaller bodies orbit. Because our observational efforts are concentrated there, we are naturally more likely to discover interstellar objects that happen to pass through this region. It's akin to searching for your keys under a streetlight simply because that's where the light is brightest. The keys might be elsewhere, hidden in the shadows, but if you don't look where the light is, you'll miss them entirely. This bias means that the fact that 3I Atlas appears nearly coplanar with the ecliptic could simply reflect the way our surveys are designed, favoring detection of objects that align with our observational focus. However, let's entertain the possibility that this isn't merely a selection bias. Imagine that there truly is something intriguing about the trajectory of this object, something that suggests a pattern beyond random chance. What makes some observers suspect that this trajectory feels almost mission-like? Consider its upcoming flyby at Mars, scheduled for October 3rd, when it will approach at approximately 0.9 astronomical units, a distance that, for an interstellar object, is quite close. While not unprecedentedly close in the grand scheme of celestial encounters, it is close enough to allow sampling of the Martian environment, its magnetosphere, the gases escaping from its atmosphere, and dust particles in its vicinity. If someone were designing a probe to study Mars remotely, a flyby at such a distance would be an ideal choice, close enough to gather meaningful data without the formidable expense and complexity of orbital insertion. From there, the object's journey continues inward toward perihelion, which it reaches on October 30th at about 0.4 AU from the Sun. This distance lies inside Mars's orbit but remains outside Earth's, providing an optimal region for solar heating without risking the disruptive tidal forces that come with getting too close to the Sun. This region is what scientists often call the sweet spot for observing a comet's activity. Enough solar warmth to activate outgassing, but not so close as to threaten structural integrity. Following perihelion, the trajectory carries the object past Venus at roughly 0.65 AU on November 3rd, then onward past Earth at about 0.8 AU on December 19th, and eventually near Jupiter at approximately 0.36 AU on March 16th, 2026. Notably, the object would sequentially pass near 3 major planets, Venus, Earth, and Jupiter, mirroring a grand tour designed to sample diverse planetary environments. If one were to craft a mission plan for a probe intended to explore multiple worlds in a single pass, these sequential encounters would be precisely the sort of trajectory envisaged. It's an architecture that hints at deliberate planning. Not necessarily a natural coincidence, but perhaps something more intentional. But before jumping to such conclusions, we must consider the concept known as the base rate fallacy. This logical trap occurs when we interpret a pattern as meaningful without sufficiently considering how likely it is to occur by chance. Yes, 3I Atlas passing near Mars, then Venus, then Earth, and finally Jupiter is an intriguing pattern. Yet interstellar space is vast, and objects can enter our solar system from countless directions with a wide range of velocities. Many trajectories are purely random, and some will coincidentally pass near multiple planets just by happenstance. We tend to notice the trajectories that fit our familiar narrative, like that of intentional exploration, because they stand out, while the myriad of other, less interesting paths go unnoticed. This cognitive bias is the same one that ensnared some researchers in the case of Oumuamua. That object exhibited a peculiar elongated shape and showed signs of non-gravitational acceleration, deviating from a purely ballistic path expected of natural bodies. Some scientists, most notably Avi Loeb, proposed that it might be an artificial light sail, a probe from an alien civilization harnessing solar radiation for movement. The suggestion was that this object might not be a natural comet at all, but rather an engineered artifact riding the solar wind, designed for exploration or surveillance. The prevailing consensus among scientists and space agencies is that the observed phenomena can be attributed to a process known as outgassing. In essence, this involves jets of gas venting from the surface of the object, acting much like tiny thrusters that can subtly alter its trajectory through space. When a comet or similar celestial body approaches the Sun, heat causes surface volatiles, substances like water ice or carbon dioxide ice, to sublimate, releasing gas that propels the object in specific directions. This outgassing creates non-gravitational accelerations, which can be detected as deviations from the expected path based solely on gravitational forces. However, in the case of the interstellar object in question, the gas itself was not directly observed. Instruments failed to detect the expected signatures of outgassing, such as specific emission lines or dust trails, which makes the hypothesis less straightforward and leaves room for skepticism. The debate over whether this absence of detectable outgassing indicates something unusual or simply a measurement limitation remains unresolved. It's a question that might never be definitively answered, especially since the window for observation was limited. The object, often referred to as Oumuamua, had already moved far beyond our reach shortly after its initial detection, leaving only a few weeks of data. In contrast, the object designated as 3I Atlas offers us a more extended observation period, spanning several months and involving multiple instruments and spectral analyses. Despite this advantage, it still presents ambiguities. Central among these is whether the object exhibits non-gravitational accelerations that cannot be fully explained by outgassing alone. Such accelerations occur when a comet vents gases asymmetrically, providing a thrust that can slightly alter its course. While this is a common phenomenon in cometary physics, the key is whether the magnitude and direction of such thrusts align with the observed gas emissions. If we observe bright jets and simultaneously measure the object's trajectory, the two should be consistent. For instance, if a prominent jet is ejecting CO2 or water vapor, we can calculate the momentum carried by that gas and predict the resulting change in the comet's orbit. This process involves precise astrometry, high-accuracy measurements of the object's position at different times before and after perihelion, which is the closest approach to the Sun. By fitting these positional data points to an orbital model, astronomers look for residuals, small deviations from the predicted path. If these residuals are minimal and match what we expect from the observed outgassing, the case remains straightforward. It's a typical comet behaving as expected. But if the residuals are large, inconsistent with the amount of gases observed, or if the direction of the acceleration points somewhere unexpected, then a puzzle emerges. Such discrepancies could suggest that some other process is at work, potentially hinting at non-natural origins or unknown mechanisms. The lesson from the earlier case of Oumuamua is instructive. Avoid overfitting limited data. Initial observations of Oumuamua included only about 20 data points over several weeks, yet scientists attempted to infer its shape, rotation, composition, and acceleration mechanisms from that sparse information. Errors tend to compound in such cases, and assumptions can lead to misleading conclusions. More data, as provided by 3I Atlas, collected over months with various instruments and spectral analyses, helps mitigate these issues, but discipline and caution remain essential. Despite the wealth of data, we cannot obtain a high-resolution direct image of the nucleus with current telescopes. Its distance and small size, possibly just a few hundred meters to a few kilometers across, make direct imaging impossible. Instead, properties must be inferred indirectly. Light curves, measurements of brightness variation over time, can estimate the object's rotation period and shape. Spectroscopy reveals its chemical makeup, while tracking subtle changes in motion can indicate non-gravitational forces at play. This indirect approach is akin to understanding a person by listening to their footsteps, voice, and shadow, rather than by observing their face directly. Based on the trajectory and physical behavior, the key question is whether this object's path suggests any intent or deliberate targeting, an idea that at this stage is overwhelmingly unlikely. The null hypothesis, that 3I Atlas is a natural comet traveling on a random interstellar trajectory, remains the most probable explanation. Nonetheless, the possibility of something more exotic cannot be dismissed outright. It is fundamentally testable. With precise measurements, we can confirm or refute the presence of non-gravitational accelerations inconsistent with outgassing, detect or rule out signs of artificial propulsion, or identify unusual chemical signatures. The data we gather, astrometric residuals, spectral lines, gas ratios, will serve as the basis for such evaluations. This leads us to an important question. Why is the U.S. military gathering at Quantico during this period? The answer is complex and involves the broader context of national security, space situational awareness, and strategic planning. While at first glance the timing might seem suspicious, coming shortly before the object's perihelion and during a period of... When this series of events unfolds, one might naturally ask, is there any genuine significance behind the timing? Or are we simply seeing a pattern where none truly exists? One of those cognitive shortcuts humans often employ to impose order on chaos. To unravel this, let's delve into what's happening at the shadowy crossroads of military and space affairs in late September 2025, focusing on the sudden and secretive gathering at the Marine Corps base in Quantico. Imagine this. Some of the most prominent figures in U.S. defense, members of the Joint Chiefs, senior Pentagon officials, individuals whose names would be familiar to those following military circles, are summoned unexpectedly to Quantico. This isn't a routine briefing or a pre-scheduled conference. Instead, it's an unusually large assembly called on short notice, described by multiple reputable outlets as both rare and abrupt. The official explanation? Vague, almost deliberately so. Strategic discussions, ongoing operations, language that offers no real insight into what's truly on the agenda, only enough to keep the details hidden. When questioned, the White House press secretary dismisses it as routine, emphasizing that such meetings happen regularly and are nothing out of the ordinary. And indeed, they do. Military leaders meet often, and these gatherings are part of the normal machinery of national security management. Yet, despite this regularity, the optics, the size of the assembly, the sudden notice, the cloak of secrecy surrounding the purpose generate a different impression, a sense of urgency. And in the realm of strategic decision-making, urgency is a powerful catalyst for speculation. It invites questions, fuels narratives, and prompts observers to connect dots that might otherwise remain separate. Media outlets from Reuters to Al Jazeera pick up the story, not as fringe rumors but as mainstream coverage. But here's the critical point. Official sources offer no concrete details. No leaked memos, no whistleblower testimonies, no on-the-record statements linking this clandestine meeting to any specific event or object. It's a conspicuous silence that leaves room for interpretation. Given this context, the question arises, are we witnessing a curious coincidence, or is there a deliberate coordination behind the scenes? The pattern that draws attention is compelling. An interstellar object making its closest approach to Mars coincides with an intense, secretive military gathering on the other side of the planet. Is it mere happenstance, or is there a connection, perhaps even an intentional one? Let's be clear. At present, there is zero public evidence directly tying the Quantico meeting to the approaching celestial visitor known as 3I Atlas. No leaked documents, no official statements, no credible whistleblowers have indicated any link. The entire association is based solely on timing, the kind of circumstantial link that, while suggestive, is inherently weak as proof. Such coincidences happen all the time in complex systems. They are a natural part of how patterns emerge from seemingly unrelated events. However, this doesn't mean the connection is irrational to consider. Human cognition is wired to spot patterns, to find meaning where it might not be immediately obvious. Space domain awareness, the military's task of tracking objects in orbit and beyond, is a serious concern for national security. The United States Space Force exists explicitly to monitor potential threats, anomalies, and unidentified objects interacting with or approaching Earth and its vicinity. They coordinate with civilian agencies, track objects with ground and space-based sensors, and analyze signals for signs of unusual activity. If an object from another star system, an interstellar visitor, were behaving in ways that raised suspicion or posed a security risk, it's entirely plausible that the military would convene a high-level rapid response meeting to coordinate observation strategies, share intelligence, and decide on next steps. Such a gathering would likely be brief, intense, and held at short notice, precisely because the event is time-sensitive. Mars's flyby window in early October is imminent, and because information sharing across agencies and commands must be synchronized carefully without revealing sensitive capabilities. In essence, if the military suspected something extraordinary about the interstellar object, be it an anomaly in its trajectory, a sign of artificial origin, or some other unknown, it would make sense to assemble the key decision-makers quickly. They would need to determine who is observing what, where, and how to interpret the data. They might also need to decide how much information to share publicly, balancing the need for transparency with the imperative of operational security. So while the current evidence is limited to coincidence and circumstantial timing, the scenario remains plausible. A sudden, secretive military gathering at Quantico could, in theory, be related to a significant extraterrestrial event, especially if the object from another star system is behaving in ways that warrant close scrutiny. But as of now, without direct evidence, the connection remains speculative, a pattern that invites curiosity but cannot be confirmed. In the grander scheme, this situation exemplifies how human minds tend to seek coherence and causation, especially in moments of uncertainty or perceived significance. Sometimes patterns are simply what this kind of high-level coordination inevitably calls for face-to-face meetings among top-level officials, especially when there's genuine uncertainty about the true nature of what's being observed. Such meetings aren't routine. They are reserved for moments when the stakes are high and the details matter. Moreover, the communication strategies surrounding these situations play a crucial role. If authorities are unsure about what 3i Atlas truly represents, and they are wary of causing public panic or diplomatic friction before obtaining conclusive information, they might craft strict guidelines about what information is appropriate to share publicly and what must remain internal until verified. This isn't an attempt at secrecy driven by nefarious motives. Rather, it's a form of prudent risk management. It's the difference between openly acknowledging that an unusual object is being monitored and actively studying it, and responsible stance, versus publicly claiming certainty when there is none, which could spark unnecessary fear or speculation. The responsible approach recognizes that a cautious stance is necessary when dealing with uncertain phenomena. When it comes to safeguarding against a threat from an object like 3i Atlas, it's important to note that it's not a threat to Earth. Its trajectory has been precisely mapped and is fully understood. There's no evidence to suggest it's headed our way, even if, hypothetically, it were on a collision course, which it absolutely isn't. Our current capabilities are woefully inadequate for deflecting or destroying an interstellar object traveling at such a velocity, about 61 kilometers per second. The recent dark mission efforts have demonstrated that we can nudge smaller asteroids out of harm's way, but only with months of warning and carefully planned interventions. An interstellar visitor moving at that speed would require years of advanced planning and technology we do not yet possess. Therefore, if there were any discussions at Quantico related to 3I Atlas, it wouldn't be about defense in the traditional sense. It would be about observation and controlling the flow of information. Such measures would aim to gather intelligence, understand the object's behavior, and prevent misinformation or panic from spreading. Another aspect that adds an intriguing layer to this scenario is the possibility of signal detection. If 3I Atlas were transmitting radio signals or showing unmistakable signs of artificial propulsion, those signals would inevitably leak out. Not necessarily immediately, but certainly over time. The global network of radio astronomers, mission scientists, and international partners would be in the loop, detecting, analyzing, and sharing data. The SETI community in particular would be abuzz with activity, scanning the skies for any signs of deliberate communication. It's important to recognize that keeping such signals secret would be nearly impossible, given the widespread, decentralized, and collaborative nature of modern astronomy. Amateur radio enthusiasts and professional observatories alike have dishes pointed at the sky, and information is shared openly across international platforms. The infrastructure simply cannot be compartmentalized in such a way that signals would stay hidden for long. Consequently, the absence of any detectable artificial signals or coordinated SETI effort strongly suggests that if 3I Atlas is indeed unusual, it isn't broadcasting its presence loudly through the electromagnetic spectrum. This silence or lack of activity in the radio domain provides a significant hint. Whatever this object is, it's not currently revealing itself as an intelligent, deliberate construct. Now, turning to alternative explanations, those that don't involve extraterrestrial artifacts. There are other plausible scenarios rooted in natural phenomena. Reports from Reuters indicate ongoing discussions about operational readiness, which could be motivated by routine bureaucratic procedures. The end of September marks the close of the U.S. government's fiscal year, a time when budgets are finalized, priorities are set, and command structures are reviewed and reorganized. These are standard administrative activities, often involving large, urgent meetings that are not unusual for this time of year. The large gathering at Quantico, therefore, could be a routine strategic planning session, rather than a response to an extraordinary event. Additionally, the geopolitical landscape remains complex. Conflicts and tensions in regions such as Eastern Europe, the Middle East, and parts of Asia require constant coordination. Such meetings are often scheduled to ensure readiness and align military and intelligence operations, regardless of what's happening in space. This broader context underscores that, while the timing may seem coincidental, these gatherings are often driven by mundane but necessary bureaucratic and strategic considerations. Amidst the complex tapestry of global tensions, ranging across multiple theaters such as Eastern Europe, the Middle East, and the South China Sea, one thing remains clear: the need for meticulous coordination and contingency planning. A gathering of military leaders and senior officials could very well be rooted in the everyday realities of geopolitical strategy and personnel management, rather than any immediate concern about mysterious space objects. Such meetings might be prompted by personnel rotations. Perhaps someone is stepping down from a critical command, or there are succession discussions underway. Alternatively, they could be driven by internal reviews or investigations that demand face-to-face deliberation at the highest levels. Importantly, none of these routine matters typically generate headlines or press releases. Rather, they spark quiet, strategic convenings. The timing of these meetings might be abrupt, accelerated by an unexpected retirement, a sudden geopolitical development requiring swift action, or shifts in budget deadlines. All these explanations are mundane at their core, often more accurate than the more exotic narratives that tend to circulate. So why does the mention of Quantico, home to a high-profile military facility, become a focal point in this story? The answer lies in the psychology of storytelling and perception. The public is likely to hear about this meeting, and ignoring it would be disingenuous, akin to pretending that the proverbial elephant in the room isn't there. The optics, the timing, the secrecy, the institutional reticence are powerful. They create an impression of a hidden connection, whether or not one truly exists. It's a classic case of narrative framing. The events are coincidental but perceived as linked because of how they are presented and perceived. The responsible approach to this situation is to recognize that Quantico's meeting happened, and that the passage of the interstellar object, known as 3I Atlas, is occurring simultaneously. Currently, these two events are only coincidentally aligned, and there is no concrete evidence tying them together. Future disclosures might change that, and if new reports emerge establishing a direct link, the story will be updated accordingly. For now, the best stance is to treat them as separate stories sharing the same timeline. However, the reason this narrative persists, and why it refuses to fade away, is rooted in a fundamental human tendency: the creation of a vacuum of information. When official sources such as NASA opt for technical blog posts instead of engaging in live press conferences, and when the military convenes in secret, offering silence rather than explanations, it leaves space for speculation. Mainstream media often reports both stories in isolation, without connecting the dots, while social media platforms eagerly fill the gaps, weaving threads of conjecture into a complex web of stories. It is precisely this lack of transparent communication that fuels the narrative's momentum. Such narratives are not harmless. They have tangible consequences. They shape public trust in institutions, influence decisions about funding and resource allocation, and color how seriously society perceives future interstellar visitors, unidentified aerial phenomena, or other unusual astronomical events. If it turns out that the comet is entirely natural and the military meeting routine, then this entire episode reveals something about how stories propagate in the absence of clear, direct communication, highlighting our collective vulnerability to speculation. Conversely, if there is more beneath the surface, if either story holds secrets that were deliberately concealed, then it becomes a lesson in the patterns of institutional disclosure and timing. Ultimately, the real story isn't just about the object from beyond our solar system. It's about the space between what is officially communicated and what the public perceives. It's about who gets to define the narrative, how that definition is conveyed, and what happens when the channels of communication are too slow or overly cautious to keep pace with the rapid flow of questions and curiosity. Filling this informational void are the amateurs, the independent observatories, the preprint servers, and the contrarian scientists. Those who have the appetite for the exotic and who tend to keep the story alive when official silence reigns. They are the ones posting raw data, running analyses, and maintaining the momentum of inquiry, often ahead of or in opposition to institutional narratives. In the current landscape of astronomical observation, the ones actively posting images, performing calculations, and keeping the narrative surrounding objects like 3I Atlas vibrant are often not the official representatives of major space agencies. Instead, they are dedicated amateurs, independent observers, and small observatories who, with modest equipment, are contributing valuable data and insights. Meanwhile, the official institutions are busy drafting their carefully calibrated, meticulously worded statements, often slow, cautious, and measured. Understanding who's watching what and how to differentiate genuine signals from background noise is crucial in this environment. Let's delve into the world of these grassroots observers, focusing on the significance of leaked data, shadow communications, and the pivotal role played by amateur astronomers, what I'll refer to as the front lines of discovery. The most striking aspect of contemporary astronomy is how accessible it has become. Gone are the days when only institutions with billion-dollar telescopes could contribute meaningful findings. Today, a good camera, a stable mount, and access to dark skies are enough, along with patience and some know-how to make a difference. The barriers that once kept entry into serious astronomical observation high have crumbled. There are now smart telescopes equipped with automation features like plate solving, which allows them to identify star patterns and match them to star catalogs automatically. These tools can tell you precisely what you're observing without extensive manual effort. Many of these systems cost less than a used car, making high-quality observational capacity available to dedicated amateurs and small teams alike. Furthermore, software for stacking images, combining multiple exposures to enhance signal and reduce noise, is often free or low cost. Online orbital mechanics calculators, which help predict the position and motion of celestial objects, are readily accessible. This democratization of discovery tools means that the process of documenting and verifying phenomena is no longer confined to elite institutions. Instead, it's a collective effort, with independent observers playing a critical role. Take the Las Cumbres Observatory Network, for example. It's a global grid of robotic telescopes operated by a mixture of professional astronomers and advanced amateurs. When 3i Atlas was first confirmed, Las Cumbres instruments were among the earliest to track it continuously. Over the following days, images, raw frames, composite stacks, and time-lapse sequences began to appear online. These weren't official press releases from NASA or ESA. They were data dumps from observers who had dedicated observation time and wanted to share their findings. Many of these images offer clear views of the comet's structure, revealing the coma, the faint sunward plume, an anti-tail phenomenon we discussed earlier, and brightness variations that suggest rotational modulation or episodic outgassing. However, the data isn't always perfect. Artifacts such as cosmic ray hits, tracking errors, and stacking misalignments can sometimes create illusions or exaggerate features. Recognizing the difference between genuine phenomena and processing artifacts is a fundamental challenge, the signal-to-noise problem. Not every image nor every observer calibrates their equipment or analyzes data in the same way. Variations in atmospheric conditions, differences in calibration procedures, and the choice of filters or exposure times all influence the final result. Consequently, when someone posts an eye-catching image of 3i Atlas exhibiting a dramatic tail or unusual tail structures, it's essential to ask, is this an authentic feature or an artifact introduced by processing? Is the image a single snapshot or a composite? What filters were used? What was the exposure time? What were the atmospheric seeing conditions? Reliable repositories and databases help answer these questions. The Minor Planet Center, for instance, publishes circulars, official notifications documenting astrometric measurements submitted by observatories worldwide. These reports are vetted, meaning they are checked against other observations and are considered trustworthy indicators of an object's position. If a measurement appears wildly inconsistent with previous data, it gets scrutinized, ensuring a baseline of accuracy. Similarly, the Jet Propulsion Laboratory's Horizon system provides predicted positions and velocities, ephemerids, based on orbital solutions. These predictions help observers plan their observations and verify whether new data aligns with expectations or if anomalies might suggest something unusual. In this landscape, amateur astronomers and independent observatories act as vital sentinels. They often detect subtle features or anomalies that might be overlooked or delayed by official channels, simply because they operate outside the bureaucratic and logistical constraints of large institutions. The key is to approach this wealth of data critically, knowing where to look and how to interpret it. Recognizing the chain of calibration, the context of each observation, and the limitations of each dataset is fundamental to separating signal from noise. In summary, the grassroots of astronomy, those with modest but capable equipment, are actively shaping the story of objects like 3i Atlas. Their open sharing of raw data, composite images, and preliminary findings plays a crucial role in the collective effort to understand these enigmatic visitors. Meanwhile, trusted repositories like the Minor Planet Center and tools such as JPL Horizon serve as anchors of reliability. As new astrometric data continues to arrive, the uncertainties surrounding the object's precise position gradually diminish, providing us with increasingly reliable and trustworthy measurements. These sources, such as the Minor Planet Center's circulars and the JPL Horizon's ephemeris outputs, are considered highly credible because they are based on carefully vetted observations and rigorous calculations. They serve as the backbone of our current understanding, giving us a solid foundation for tracking the object's trajectory. In addition to these established sources, there are preprints, early versions of scientific papers posted on platforms like the Archive server, where astronomers share their latest findings before they undergo formal peer review. This process, peer review, can often take months, and in the fast-paced realm of comet observation, the object might have already moved on or become unobservable by the time a peer-reviewed paper sees publication. Preprints are especially crucial in such scenarios because they allow the scientific community to share timely insights quickly. The recent JWST spectroscopy result we've referenced exemplifies this. While it is a preprint and not yet peer-reviewed, it was authored by members of the mission team, scientists directly involved with the instrument and the data analysis, whose reputations depend on getting the science right. This association bestows the preprint with considerable credibility, making it almost as trustworthy as peer-reviewed work, even though it remains preliminary. It's not gospel, of course, but it's close enough to inform our understanding and guide further investigation. However, the landscape is cluttered with noise, misleading images, unsupported claims, and speculative theories that spread rapidly through social media and online forums. These include screenshots of unattributed images, assertions of a giant nucleus based on misinterpreted brightness measurements, and guesses about the object's mass derived from incomplete astrometric data. Videos featuring ominous music and no credible sources are also common. These pieces of misinformation propagate quickly because they evoke emotional reactions, fit narratives that resonate with certain beliefs, or are simply more shareable than dry scientific data. The contrast is stark. A straightforward link to the Minor Planet Center circular or an official ephemeris is not as compelling or sensational as a viral post filled with speculation. This brings us to the importance of understanding visual gotchas, the tricks and illusions that can lead to misunderstandings about what's actually observed. A prime example is anti-tails and projection effects, which are often mistaken for physical anomalies. When observing a comet, what we see is a three-dimensional structure projected onto a two-dimensional sky map. The dust tail, which is pushed by solar radiation pressure, streams outward along the comet's orbital path. Depending on your viewing angle, this tail can appear to curve, bend, or even point sunward, an optical illusion caused by perspective, not a violation of physics. A famous historical example is Comet Aaron-Rowland in 1957, which displayed a tail that seemed to be pointing directly toward the sun. It was later understood to be simply the edge of a dust sheet seen at a nearly tangential angle, an illusion of perspective. The same phenomenon explains some of the strange images of 3i Atlas. Without proper context, knowing the phase angle, the dust scattering properties, or the three-dimensional geometry, you might interpret a particular tail's shape as something unusual or even artificial. To truly understand what you're looking at, it's essential to know the phase angle, the angle between the sun, the object, and your vantage point. This helps determine whether the tail's appearance is a projection effect or a physical feature. Dust scattering models can simulate how light interacts with the particles, allowing us to reconstruct the structure in 3 dimensions and then project it onto the sky as seen from our perspective. Alternatively, one can simply glance at the image and react instinctively, exclaiming, "Sunward tail, that's weird," and sharing it without further context. Unfortunately, that's often what happens. The more common approach is the latter, which can lead to misinterpretation. For those who want to follow the observations closely, learning how to read an ephemeris becomes invaluable. Tools like JPL Horizons allow you to plug in the target, here, 3i Atlas. Set your observation site and date range, and generate a detailed table of positional data. The key columns include the Sun-Comet distance in astronomical units, AU, the observer-comet distance, also in AU, the Sun-observer target angle, which indicates the phase angle, and the solar elongation, the angular distance between the Sun and the object in the sky. When the solar elongation drops below about 20 degrees, observing from the ground becomes increasingly difficult. This is because the comet appears very close to the Sun in our sky, making telescopic observations challenging or even unsafe due to scattered sunlight and potential damage to sensitive equipment. Small changes in the Sun object distance or the observer object distance are significant because of the inverse square law. The brightness and apparent size of the object follow a quadratic relationship with distance. So, as the brightness of a comet diminishes proportionally to the square of its distance from us. In practical terms, this means that a comet situated at 1 astronomical unit, roughly 150 million kilometers from the Sun, appears 4 times brighter than the same comet positioned at 2 astronomical units, assuming all other factors remain constant. However, in reality, all else is rarely equal when it comes to comets. Their apparent luminosity isn't just dictated by their proximity, it's heavily influenced by their activity levels, which increase as they draw nearer to the Sun. This activity primarily manifests through outgassing, the process where volatile substances like ices sublimate and release gas and dust into space, causing the comet to brighten beyond what simple distance calculations would suggest. Disentangling the effects of proximity versus activity requires meticulous measurement over multiple points in time, or what scientists call multiple epochs. This is where coordinated amateur observation campaigns come into play, exemplifying real, rigorous science. Networks of dedicated observers work simultaneously, capturing images on the same nights, employing consistent filters and using standardized calibration stars. By doing so, they compile detailed light curves, graphs that show how a comet's brightness changes over time. These light curves are fundamental tools. They allow scientists to analyze and understand the physical and compositional properties of a comet with accuracy and reproducibility. The best amateur campaigns take this process seriously. They employ stacking techniques, combining multiple images to reduce noise and enhance faint features, and use aperture photometry, a method that measures brightness specifically of the nucleus region, minimizing interference from surrounding coma or dust. They also carefully account for atmospheric extinction, which is the dimming of celestial objects caused by Earth's atmosphere. These are not casual snapshots taken with a phone camera. They are methodical, systematic observations that adhere to scientific standards. When conducted with precision, this data becomes highly valuable and can be published in scientific journals. Yet complications arise when we consider the amplification problem, an issue that introduces significant complexity into interpretation. For instance, a detailed analysis might reveal that a comet has a rotational period of roughly 14 hours. With episodic increases in brightness that suggest localized jets, outgassing regions that erupt sporadically. Such findings are credible and scientifically meaningful, but they often fail to generate headlines. Instead, sensational versions emerge, stories claiming the comet is behaving erratically or even suggesting it might be an alien probe. These narratives tend to go viral, infiltrating social media, Reddit threads, YouTube videos, and Twitter discussions, where they drown in a flood of noise and speculation. Given this environment, it's reasonable to predict that during periods when ground-based telescopes are unable to observe the comet, such as during the Earth's blackout period caused by solar conjunction, more leak images from Mars orbiters will surface. When Earth's view is obstructed, the only vantage points available are spacecraft orbiting Mars or perhaps some solar observatories, creating a significant information vacuum. And as history shows, vacuum tends to be filled. Someone will likely post an image claiming it is from Mars Express or the Trace Gas Orbiter, supposedly revealing something anomalous or extraordinary. However, before accepting such claims outright, critical evaluation is essential. First ask, is there accompanying metadata? Is there a clear timestamp indicating when the image was taken? Does the resolution and spectral range of the image match what the instrument is capable of? Has there been any official confirmation or attribution from the European Space Agency or the mission teams? Most often, these images turn out to be fake, misattributed, or genuine, but from a different mission altogether. The standards for evidence must be high, especially when official channels are silent. For those following these developments responsibly, the core advice remains. Rely on sources with verifiable authority. This includes official updates from the Minor Planet Center circulars, the JPL Horizons Ephemeris, preprints from reputable servers like RXIV, and official posts from ESA and NASA. When encountering dramatic claims, always request the underlying data and methodology. Cross-check findings with other observers and datasets. If the claim is valid, it should be reproducible. If it's noise or artifact, it will stand out as an anomaly or outlier. It's important to remember that spectacular claims do not necessarily equate to accuracy. The most reliable data often comes from seemingly mundane measurements. Precise astrometric positions, spectral lines matching expected volatile signatures, or null results that dismiss exotic hypotheses. These boring data points are the foundation of scientific integrity, providing the solid baseline against which extraordinary claims can be judged. Ultimately, careful, disciplined observation and verification are the best defenses against misinformation in this complex and rapidly evolving field. Science advances as much by systematically ruling out what something is not as by definitively confirming what it is. Yet a perplexing question arises. Why are the major institutions so notably silent about the recent interstellar visitor, 3I Atlas? Is this silence rooted purely in a cautious scientific approach, or does it hint at a deeper, perhaps security-related motive that we're not immediately aware of? To understand this, we need to delve into the underlying culture and protocols that govern agencies like NASA and their counterparts worldwide. Let's begin with the most straightforward explanation, one rooted in the traditional scientific culture that has shaped these organizations over decades. The reason they are reticent is primarily due to a deeply ingrained error avoidance philosophy. These agencies have long memories of past missteps which have informed their current cautious stance. For example, in 2011, CERN's announcement of faster-than-light neutrinos was later proven to be a loose cable. It was a false alarm that caused a media frenzy, only to be corrected after meticulous investigation. Similarly, the initial excitement over arsenic-based life forms, later revealed to be contaminated samples, underscores how premature claims can backfire. Each of these episodes reinforces the institutional tendency to demand overwhelming, incontrovertible evidence before broadcasting any extraordinary claims. The process of confirming something as groundbreaking as an interstellar object passing through our solar system involves multiple observation epochs. It's not enough to have a single snapshot or a handful of data points. The data must be robust enough to characterize the object's orbit with precision. This entails ruling out measurement errors, such as inaccuracies in tracking or background star contamination, and fitting complex models that include non-gravitational forces. Since outgassing jets or other subtle effects can influence a small body's trajectory, scientists need data from before and after perihelion to detect and quantify these forces. One or two data points simply are insufficient. A thorough understanding might require dozens or even hundreds of measurements, each with their own uncertainties. Given this, the natural institutional response is patience, to wait, gather more data, and subject findings to rigorous peer review before making any bold public statements. Adding to the cautious approach is the reality of bureaucratic processes. Communication within large organizations like NASA is inherently slow, not because of any intent to conceal but due to procedural rigor. Each piece of information passes through multiple layers: scientists, legal advisors, international partners, and public affairs officers, each of whom must ensure that the message is accurate, unambiguous, and aligned with policy. A single blog post, for example, might require 5 rounds of review before it is published. This is not suppression, but a safeguard against inadvertent misinformation that could cause unnecessary alarm or misunderstandings. It's about ensuring that what is communicated is reliable, especially when dealing with phenomena that could be mistaken for threats or misunderstood as evidence of extraterrestrial activity. In this context, it's worth noting that NASA has indeed shared some updates related to 3I Atlas, such as preliminary observations from the Hubble Space Telescope and links to the latest preprints from the James Webb Space Telescope. Yet they have not staged a media spectacle. This measured approach might be entirely appropriate because at this stage the data is still preliminary and not yet conclusive. The agencies are aware that interesting does not necessarily mean urgent or extraordinary enough to warrant a press conference. They are still in the process of collecting and analyzing data, and they recognize the importance of getting it right before making any definitive claims. Now, shifting to the more speculative realm, we must acknowledge that some of the reasons behind institutional reticence might involve security considerations, though these are less openly acknowledged. Space domain awareness, the ability of a nation's military and intelligence agencies to monitor objects in orbit and beyond, is a real, well-established practice. The U.S. Space Force, along with other national space programs, actively tracks objects in Earth orbit, near-Earth space, and even interplanetary space. This tracking helps them identify potential threats, monitor space debris, and maintain situational awareness. Given this context, it's conceivable that agencies are weighing the potential security implications of a nearby interstellar object, especially if it exhibits characteristics that could be interpreted as unusual or potentially threatening. For instance, if the object's trajectory or behavior suggests it might be a probe or a craft, whether natural or artificial, some agencies may prefer to keep their observations classified or limited until they understand precisely what they are dealing with. Such caution would be consistent with protocols for handling unidentified or ambiguous space objects, especially when their origins and capabilities are uncertain. Furthermore, the existence of classified military assets and sensors that monitor space activity adds another layer to this discussion. It's possible that some observations are being made by military satellites or ground-based radar systems that are not yet declassified or publicly disclosed. These assets could be gathering data that, for national security reasons, are not immediately shared with the public or even with civilian scientists. In this scenario, the apparent silence from agencies like NASA could be a deliberate choice. Space situational awareness is a sophisticated and multi-layered process involving the diligent monitoring of satellites, space debris, asteroids, and any celestial or artificial objects that could pose a threat or necessitate coordinated action. When an unusual object enters our solar system and follows a trajectory that brings it close to Earth or its vital assets, it is promptly flagged. This alert isn't necessarily because the object is deemed dangerous. Rather, it is flagged because it is anomalous, something that deviates from the norm and warrants attention. Anomalies, after all, are what draw the eyes of those responsible for tracking potential space hazards, whether they are natural or artificial in origin. Despite all this, there is no publicly available indication that the interstellar object known as 3I Atlas has prompted a military or defense posture. Let me emphasize that point again. There is no official public evidence to suggest that the defense or intelligence communities have taken any extraordinary measures or have issued any formal statements regarding this object. There have been no briefings from the Space Force, no congressional hearings, no classified memos or leaks suggesting a heightened alert or security concern. If the object were being treated as a potential threat, or if it required secretive analysis, we would expect to see tighter, more comprehensive control over information. More signs of covert activity, in other words. Instead, the available evidence, the preprints from JWST, the posts from Hubble, the observation plans from the European Space Agency, all point to a scenario of openness and ongoing scientific investigation, which argues against the notion of a security lockdown. However, the situation becomes murky when we consider the principle that absence of evidence is not evidence of absence. Just because we do not see clear signs of security involvement does not mean that such measures are not in place. It simply means that if they exist, they are hidden from public view, operating behind the scenes in ways that we cannot observe. This creates a fertile ground for speculation, as the gap between what is observable and what might be happening beyond our line of sight becomes a space where conjecture thrives. To illustrate, consider the case of the interstellar object known as Oumuamua, discovered in 2017. Initially, there was no indication of military or security agency involvement. It was a civilian discovery made through public observation campaigns and analyzed by scientists outside the defense community. Avi Loeb's controversial hypotheses, suggesting that Oumuamua might be an artificial probe, gained attention, but these ideas remained within the realm of academic debate rather than classified security concerns. Contrast this with the more recent UAP, unidentified aerial phenomena, reports released by the Pentagon in 2023 and 2024. These included videos captured by Navy pilots of unexplained aerial objects, which were explicitly framed as defense issues. The key difference here is their domain. UAPs are atmospheric phenomena observed within Earth's vicinity, involving military and civilian authorities in the same jurisdiction. They are a different category altogether than distant astronomical objects like 3I Atlas, which are billions of kilometers away from Earth and outside our immediate operational domain. So if there is a security dimension to 3I Atlas, what might it look like? It's likely not overt or publicly acknowledged. Instead, it could involve classified sensors and measurements, additional data collection that is not shared publicly due to sensitivity. Coordination might be taking place between civilian space agencies such as NASA and ESA and military space surveillance assets, with certain information restricted. Not because it is classified as military or intelligence data per se, but because the methods and instrumentation used to gather it are sensitive and could be reverse-engineered by adversaries. The challenge, of course, is that much of this operational activity is indistinguishable from routine procedures. Civilian and military agencies coordinate regularly. NASA shares tracking data with the Space Force and instrument capabilities, including spectral ranges and signal processing techniques, are often sensitive not because of what they observe, but how they observe it. These details could be exploited by others to gain insight into surveillance methods or technological capabilities. Bureaucratic procedures further complicate transparency. Before a formal statement can be issued, agencies often require sign-offs from multiple entities. NASA, the European Space Agency, the National Science Foundation, and the Department of Defense, each with their own review processes, priorities, and risk tolerances. This naturally results in delays and a cautious approach to releasing information publicly. All of this means that the absence of overt security activity does not necessarily equate to a lack of concern or covert operations. It simply indicates that much of the activity remains behind closed doors, cloaked in layers of bureaucratic and operational secrecy. The real challenge is not whether such measures are being taken, but understanding that their existence is often concealed, and that this concealment fuels further speculation. In summary, while space vigilance is a continuous and systematic effort, there is currently no public evidence that 3i Atlas has triggered a security response or elevated threat level. The lack of transparency, however, leaves room for guesswork and conjecture, precisely where. During this critical period, the strategic approach to information sharing becomes evident. A statement from NASA indicating that they are comfortable with the current data might inadvertently reveal more than intended, potentially hinting at knowledge the Department of Defense would prefer to keep classified. Conversely, if scientists within the European Space Agency express a desire for additional data before committing to definitive statements, their cautious stance might be perceived as hesitancy or even suspicion. Faced with these contrasting pressures, the prudent choice for agencies is often to produce neutral, non-committal language. Standardized, bland statements that satisfy all parties without stirring controversy or premature speculation. This approach ensures that no single stakeholder feels exposed or vulnerable. But it also results in a communication style that is notably unexciting, devoid of the dramatic flair that captures public attention. The alternative is to wait patiently until the accumulating data force a clear conclusion. This delay, however, is not merely a matter of scientific rigor. It also involves strategic considerations related to funding and resource allocation. For instance, both the James Webb Space Telescope and the Hubble Space Telescope are heavily oversubscribed. On average, for every hour of telescope time that is granted, approximately 10 proposals are rejected. This highly competitive environment means that mission scientists and observatory managers must carefully manage expectations. Overpromising on a target that might turn out to be insignificant or unremarkable could lead to a waste of valuable observation slots and diminished trust in future proposals. Furthermore, claiming to be able to produce detailed images of the comet's nucleus when the data collection capabilities are limited would be irresponsible. It is much better to set realistic expectations, emphasizing that the data will speak for itself without overpromising. This cautious stance ensures the scientific integrity of the project and prevents the disappointment that accompanies unmet expectations. Now, shifting into the realm of speculation, one plausible hypothesis is that the language surrounding the interstellar object designated 3i Atlas is being deliberately sanitized or scrubbed. The purpose of this would be to avoid implying any intentionality, whether agency, deliberation, or design, until after the perihelion data has been thoroughly analyzed. For example, describing the object as simply making a close pass of Mars is a straightforward factual statement. It implies a natural trajectory and leaves open the question of origin or purpose. In contrast, suggesting that the object is targeting Mars introduces a narrative of agency, suggesting a deliberate mission or design, which carries far more implications, potentially even extraterrestrial intent. This distinction is crucial because the phrase targeting Mars is loaded with assumptions of purpose and consciousness. If the true nature of the object remains uncertain, the most cautious approach is to adhere to neutral, fact-based language until the data provides clarity and the hypothesis can be tested. Another layer of strategic silence is evident in how agencies handle the Earth-side blackout. Periods when observational capabilities are limited or entirely unavailable, particularly during perihelion when the object passes very close to the Sun from our vantage point. During this time, it is logical to avoid generating false expectations for real-time updates. If the data cannot be observed or accurately interpreted because of solar glare or instrument limitations, it is more responsible to remain silent. This silence is not necessarily indicative of concealment, but is a prudent decision to prevent misinterpretation or premature conclusions. Instead, agencies are likely to focus on collecting high-quality, comprehensive data during the period when the object is observable again, after the sun's glare diminishes and the instruments can re-engage. By waiting to release a complete picture, they avoid the pitfalls of trying to interpret incomplete or ambiguous data in real time, which could lead to errors or the need to retract earlier statements. This approach underscores a fundamental truth. The absence of sensational drama in official communications does not mean an absence of data. Quite the opposite. It may reflect an environment where a vast amount of information is being meticulously gathered and analyzed behind the scenes. The institutions involved are often overwhelmed by the volume of data, which makes public communication a secondary priority. An acknowledgement that the real work is happening in the laboratory, control rooms, and data centers away from the public eye. For those who seek to understand what is truly unfolding, the most reliable sources are the preprints posted on scientific servers, the detailed logs maintained by mission teams, and the schedules of observations. These raw, unfiltered records provide insights that official press releases, which are designed to be accessible and digestible, often lack. Ironically, while Earth-based telescopes go dark during perihelion, Mars becomes the most vital observation point in the solar system, even if only temporarily. The Martian orbiters, specifically ESA's Mars Express and the ExoMars Trace Gas Orbiter, become humanity's frontline witnesses. These spacecraft, in orbit since 2003 and 2016 respectively, are primarily tasked with studying Mars, its surface, atmosphere, and geology. Nonetheless, they are equipped with instruments capable of turning their gaze outward toward passing objects like TRI. Let's delve into the capabilities of the instruments aboard the Mars orbiters during the upcoming observational window from October 1st to 7th. The Trace Gas Orbiter, or TGO, is equipped with two key tools. NOMAD, which stands for Nadir and Occultation for Mars Discovery Instrument, and the Atmospheric Chemistry Suite, or ACS. Both are high-resolution spectrometers meticulously designed to detect and analyze trace gases within the Martian atmosphere. Their operational wavelengths span both infrared and visible spectra, enabling them to identify distinct spectral signatures of molecules such as water vapor, methane, carbon dioxide, and carbon monoxide. When these instruments are directed toward a comet, they can gather similar data, determining the composition of the coma, estimating gas emission rates, and even analyzing isotopic ratios, contingent upon the strength of the signals received. Meanwhile, the European Space Agency's Mars Express carries its own suite of instruments tailored for detailed analysis. SPICAM, or spectroscopy for investigation of characteristics of the atmosphere of Mars, is one such tool alongside Omega, a visible and infrared imaging spectrometer. Omega is capable of constructing detailed maps of the surface by examining how different wavelengths of light are absorbed or reflected by various materials. When pointed at a comet's coma, Omega can produce spatially resolved maps that detail gas distribution, dust scattering properties, and temperature gradients across different regions. During the observation window in early October, these instruments will primarily focus on gathering time series spectra, repeated measurements of the comet's coma over several days. This approach allows scientists to monitor how the coma's composition evolves as the object approaches the sun and experiences increasing thermal activity. They might detect episodic outbursts, such as sudden brightness spikes or localized jets that have been reported by ground-based observers. For instance, a quick surge in carbon dioxide, water vapor, or carbonyl sulfide emission could indicate active vents turning on and off, a phenomenon that would support models like the thermal wave hypothesis or patchy nucleus scenarios. Furthermore, these instruments can analyze dust scattering phase curves. As the geometry between the sun, the comet, and the spacecraft changes, the brightness of dust particles varies depending on the scattering angle. Small particles tend to scatter sunlight more intensely in the forward direction, making the dust appear brighter when the sun is behind the observer, whereas larger or differently composed particles exhibit backscattering behavior. By measuring the brightness at various phase angles, scientists can infer the size distribution of dust grains, information that reveals surface properties of the nucleus and how violently it's shedding material. However, despite these capabilities, there are fundamental limitations to what the orbiters can achieve. Most notably, they cannot resolve the nucleus directly. Even from a distance of 30 million kilometers, roughly the same as an orbit around Mars, the nucleus, which is at most about 5.6 kilometers across, appears as an exceedingly tiny target. To put this into perspective, the best imaging camera aboard Mars Express has a resolution of about 10 meters per pixel when observing the Martian surface. At 30 million kilometers, this translates to each pixel covering hundreds of kilometers, rendering the nucleus essentially a point source, indistinguishable from a distant star. While the coma may exhibit spatial structures such as brightness gradients or hints of jets, the nucleus itself remains hidden from direct imaging. Additionally, these instruments are not capable of capturing rapid or transient features like microjets or sudden outbursts with high temporal resolution. Their design favors slow, methodical scans rather than quick, targeted observations of moving objects. Consequently, any fleeting activity occurring on timescales shorter than their observation cadence would likely go unnoticed. Collectively, the limitations stem from the instrument's primary purpose, to study the Martian atmosphere and surface in a steady, systematic manner, rather than to perform rapid, close-up cometary imaging. While it's possible to repurpose the instruments on these spacecraft, several significant limitations inevitably come into play. These include data transmission rates, the agility of the spacecraft's pointing mechanisms, and the amount of observation time that the mission operations teams are willing to allocate. It's important to recognize that this is not a dedicated flyby mission purpose-built with instruments optimized specifically for studying 3I Atlas. Instead, these are opportunistic observations, tools designed primarily for other objectives, being temporarily redirected to capture data when the opportunity arises. Another critical factor is the data transmission pathway itself, which is more consequential than many might realize. The orbiters do not maintain continuous contact with Earth. Instead, they store the collected data on board and transmit it during scheduled communication windows. This setup introduces inevitable delays, sometimes spanning hours, sometimes even days, between the moment the observations are made and when the data arrives on Earth for analysis. Following data collection, the process of calibration and processing begins. Raw spectroscopic data must undergo several steps: wavelength calibration to ensure accurate spectral measurements, background subtraction to remove noise and artifacts, and comparison against reference spectra to identify the chemical signatures. Each step takes time, especially considering the volume of data and the need for meticulous verification. Consequently, even if the James Webb Space Telescope's observations on August 7th reveal something significant, the processed and calibrated results might not be available until mid-October, late October, or even early November. The European Space Agency has been transparent about this process through their frequently asked questions pages, emphasizing that observation planning, data collection, and analysis all follow a deliberate, systematic timeline. They make it clear that there are no promises of real-time updates or live feeds, only careful, patient science conducted according to the pace that rigorous research demands. This approach is rooted in ensuring accuracy and reliability, even if it means a delay before the public or scientific community can fully interpret the findings. At Mars, additional assets could potentially contribute to observations, though their involvement remains uncertain. NASA's Mars Atmosphere and Volatile Evolution, MAVEN orbiter, for instance, studies the upper atmosphere of Mars and how solar wind interacts with and strips away atmospheric particles. MAVEN is equipped with ultraviolet instruments capable of detecting emissions from the coma of 3I Atlas, such as atomic hydrogen from water dissociation, as well as carbon, oxygen, and other lines, potential indicators of outgassing activity. However, MAVEN's instruments are optimized for detecting faint extended sources like atmospheric glow phenomena, rather than point sources such as comets. This specialization raises questions about its capacity to contribute meaningful data during the flyby. Similarly, Mars Reconnaissance Orbiter, MRO, which boasts high-resolution cameras, faces a fundamental challenge due to the vast distance, about 30 million kilometers, making resolution a significant obstacle. At that range, the resolution is insufficient to resolve detailed features of the comet. But MRO could still potentially detect the object as a point of light, confirm its position, and contribute to astrometric measurements. The same applies to Mars Odyssey. Yet none of these missions have announced definitive observation plans for this specific event, placing us in a realm of possibility rather than certainty, territory where success depends heavily on timing and geometric alignment. One intriguing, though highly speculative, scenario involves the possibility that 3I Atlas experiences a major outburst during the Mars observation window. If the comet's brightness increases substantially, by a magnitude or more, the orbiters could potentially detect the chemical signature associated with such an event. This might include a sudden flood of carbon dioxide, a burst of water vapor, or the appearance of trace species like sulfur dioxide or ammonia that were not present before. Such a detection would be invaluable. Observing such an outburst would provide direct evidence that the nucleus is not uniform but contains buried volatiles or pockets of different compositions that become exposed during activity. This would lend strong support to models proposing a heterogeneous crust and would help rule out simpler, uniform composition scenarios. In addition to the orbiters orbiting Mars, the European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, offers a tantalizing possibility. Although currently en route to Jupiter and primarily designed to study the icy moons of that planet, JUICE remains relatively close to Earth's inner solar system. If conditions allow, it might attempt distant observations of 3I Atlas in early November after the comet's perihelion passage. However, given the instrument suite of JUICE, tailored for the environment around Jupiter rather than small, distant comets, its ability to contribute meaningful data during this flyby remains uncertain. Any observations would likely be limited to broad detections or indirect clues, and the results might not be available until many months later, possibly not until 2026. In summary, while the orbiters at Mars hold the potential to gather valuable, if limited, data during this critical window, their capacity is constrained by technical and operational factors. Nonetheless, any signs of a major outburst or compositional shift detected by these assets would be a scientific boon, certainly, Here's a deeply expanded, polished, and cohesive version of the provided excerpt, emphasizing clarity, flow, and detail. The European Space Agency's JUICE mission, with its suite of sophisticated instruments, is primarily tailored for studying Jupiter and its many moons. These instruments are optimized for analyzing the thick atmospheres, magnetic fields, and surface compositions of the gas giant and its satellite system, not for tracking small, faint comets from a vast distance of tens or even hundreds of millions of kilometers. Observing a tiny celestial object, such as a comet, from such an extreme range is inherently challenging. The faint glow, the weak signals, and the limitations of the onboard sensors mean that any data collected will be of limited resolution and clarity at best. Even if the JUICE spacecraft attempts to observe 3I Atlas during its flyby, the chances of capturing detailed, high-quality imagery or spectra are slim. Moreover, the sheer distance involved implies that the data, once gathered, will take a significant amount of time to reach Earth and be processed. This delay, known as downlink latency, is an unavoidable factor in space communications. For JUICE, the process of transmitting data back to Earth, analyzing it, and then releasing results might stretch well into the year 2026. This means that scientists and observers on Earth may not see the full picture for many months after the event. The practical consequence of this delay is that, in early October, during the comet's closest approach to Mars, Earth-based telescopes and space observatories in low Earth orbit will be largely unable to observe 3I Atlas due to solar glare and positional constraints. During this critical window, Mars's orbiters become our primary eyes in the sky. They serve as our forward-deployed scientific outposts, providing vital data on the comet's activity, composition, and behavior. However, it's important to recognize that these Mars orbiters won't be able to provide the stunning close-up images that capture the public's imagination or generate headlines. They are not designed to produce high-resolution detailed photographs of tiny comet nuclei from hundreds of millions of kilometers away. Instead, their strength lies in analyzing the chemical makeup of the comet's coma, the glowing cloud of gas and dust surrounding its nucleus, tracking how this composition evolves over time, and confirming or refuting models of the comet's behavior and structure. This kind of data, spectroscopy, time series measurements, and chemical signatures, is the foundation of scientific understanding. It allows scientists to test hypotheses about the comet's formation, its internal layering, and its volatile content. Yet this approach introduces a new challenge, the emergence of a data gap after Mars completes its observation window, which lasts from early October through the first week of November. Earth's telescopes will be unable to observe the comet directly for an extended period. The reason isn't due to technical failure or conspiracy, but stems from the fundamental geometry of our solar system and the position of the Sun. During this interval known as solar conjunction, the comet will be passing very close to the Sun's line of sight from Earth's perspective. The angular distance, the solar elongation between the comet and the Sun in our sky, will fall below the safety threshold for ground-based telescopes, making direct observation impossible. Pointing telescopes too close to the Sun risks saturating the detectors with scattered sunlight, which can damage sensitive instruments. Even space-based observatories, despite their shielding, face strict constraints. The Hubble Space Telescope, with its massive sun shield, cannot look within 50 degrees of the Sun. The James Webb Space Telescope, equipped with an enormous sun shield to protect its instruments from solar heating, has even more restrictive pointing limitations. As a result, during this period we go effectively blind, unable to track or study the comet visually or spectroscopically, until the Sun's glare diminishes enough in early December. This phenomenon isn't new. History provides many examples of comets that have experienced similar observational blackouts at perihelion, the point in their orbit closest to the Sun, especially those on sun-grazing trajectories. Such comets often come very close to the Sun's corona, the blazing outer atmosphere, and reach their peak brightness during this perilous passage. The comet of the century, Comet Ison in 2013, served as a recent example. It was anticipated to brighten dramatically as it skimmed the Sun, with predictions of a spectacular display. Unfortunately, when it reached perihelion, it disintegrated, breaking apart under the intense thermal and tidal stresses, before we could observe its final moments from Earth. Most of that dramatic evolution took place behind the Sun's glare. We only saw the aftermath, a fading dust cloud, the remnants of what once promised to be a magnificent comet. The solar observatories, such as the Solar and Heliospheric Observatory, SOHO, and the Solar Terrestrial Relations Observatory, STEREO, have played crucial roles in witnessing these events. They can operate during the Sun's intense glare because 3I Atlas is not a sun grazer. Rather, it approaches perihelion at approximately 1.4 astronomical units from the Sun, positioning it well outside the zone where tidal forces could threaten its integrity. This distance, while still relatively close in cosmic terms, is comfortably within a safe margin that prevents the comet from suffering disruption due to gravitational stresses. However, the critical juncture, the moment when solar heating reaches its peak, and volatile activity should be at its maximum, occurs while our planet's view is largely obstructed, rendering Earth-based observations largely ineffective. During this perihelion passage, what instruments remain capable of capturing any meaningful data? The answer lies in specialized space-based observatories designed to operate in the challenging environment near the Sun. The Solar and Heliospheric Observatory, or SOHO, equipped with coronagraphs that mask the Sun's bright disk, can observe the surrounding corona and detect objects passing through this region. If 3I Atlas is sufficiently bright and positioned favorably, SOHO might spot it as a faint point of light moving across its field of view. Nevertheless, SOHO's design is optimized for studying solar phenomena, solar wind, coronal mass ejections, and sun-diving comets, not detailed comet spectroscopy. Its spatial resolution is relatively coarse, and its spectral capabilities are limited, providing only broad overviews of dynamic behavior such as brightening, fading, or fragmentation, but not precise chemical compositions or fine structural details. Similarly, the Solar Terrestrial Relations Observatory, or STEREO, comprises two spacecraft orbiting the Sun at different vantage points, offering a stereoscopic perspective. During conjunction, when the comet aligns behind the Sun from Earth's perspective, STEREO could help determine the three-dimensional position and motion of 3I Atlas, constraining its trajectory and velocity. Yet like SOHO, STEREO's resolution and spectroscopic capabilities are limited. Observations would mainly capture the comet's silhouette against the solar background, revealing its behavior in outline rather than in vivid color or detailed composition. Adding to this fleet of observation tools, the Parker Solar Probe, which ventures deep into the Sun's corona on its own mission to study solar phenomena, has imaging equipment designed for solar observation, not for distant comets. Its cameras are optimized for capturing the Sun's energetic environment, and they lack the resolution and spectral sensitivity needed to analyze a comet at hundreds of millions of kilometers away. The same applies to the Solar Orbiter, a billion-dollar mission focused on solar physics. While these spacecraft might incidentally observe 3I Atlas passing through their fields of view, capturing it in passing is far from their primary objective, and detailed analysis of the comet's chemistry or structure is not within their operational scope. Given these limitations, the overall scenario from late October through November becomes one of observational darkness. Our direct view of 3I Atlas is significantly compromised, reducing us to observing shadows rather than substance. We must rely on indirect measurements and inferences which inherently leave open the possibility for unobserved phenomena, fragmentation, outbursts, or other dramatic changes that occur off camera. One clear possibility is fragmentation. If the nucleus is a loosely bound rubble pile, held together by a fragile combination of self-gravity and ice, thermal stresses at perihelion could induce cracks or even cause the nucleus to split apart entirely. This phenomenon is not without precedent. The famous comet Shoemaker-Levy 9 disintegrated into multiple fragments before colliding with Jupiter, and comet 73P Schwarzmann-Wachmann has broken into dozens of pieces over successive perihelion passages. In the case of 3I Atlas, if such a breakup occurs, we might not recognize it immediately. We could re-establish observational contact in December and find the original singular nucleus replaced by a scattering of fragments or a diffuse cloud of debris, rather than a well-defined compact coma. This outcome would answer many questions about the internal structure of the comet, revealing whether it was a fragile assemblage or a more cohesive body. Yet it would also mark the end of the object as a single, coherent target for continued study. Another scenario involves rapid rotation changes driven by asymmetric outgassing jets. These jets can exert torque on the nucleus, spinning it up or slowing it down. If the comet's jets are unevenly distributed and fire while we are blind to the process during perihelion, the nucleus's rotational state could be dramatically altered without our immediate knowledge. Such changes would manifest later in the post-blackout phase as variations in the light curve, alterations in the periodic brightness oscillations. A different rotation period or a change in amplitude would suggest that the nucleus is tumbling or spinning irregularly, possibly due to the uneven outgassing forces acting upon it during perihelion. Detecting these changes would provide insight into the internal and surface properties of the comet, revealing whether it is structurally stable or prone to rotational instability. In essence, during this critical window of perihelion, our observational capabilities are limited, and the most critical aspect of this entire journey revolves around what scientists refer to as the non-gravitational kick. This subtle but telling motion change is what everyone is eager to measure as the comet approaches its perihelion, the closest point to the Sun in its orbit. When a comet vents gas asymmetrically, meaning more gas escapes from one side than the other, it experiences a gentle acceleration, a push that nudges its trajectory ever so slightly. Though this acceleration might amount to just fractions of a kilometer per hour, over the span of weeks and months, these tiny pushes accumulate, gradually shifting the comet's orbit in a way that can be detected with precise measurements. By comparing the comet's position before perihelion, obtained through meticulous astrometric observations, and its position after the blackout period when data collection resumes, astronomers can detect these minute kicks. These measurements allow us to infer the pattern of outgassing, the way gas is escaping from the comet's surface, which in turn reveals details about its internal composition and activity. If the magnitude and direction of this velocity change align perfectly with the observed gas production, then the case is simple. It's a regular natural comet behaving as expected. However, if the measured kick turns out to be too large, or if it's in an unexpected direction, or if it cannot be plausibly explained by known jet activity, those streams of outgassed material, we face a dilemma. This presents us with a genuine scientific challenge. Either the comet is exhibiting unusual behavior that demands new explanations, or perhaps something more exotic is at play. On the other hand, if the data reveal no significant or unusual acceleration, the story remains straightforward. The comet could pass through perihelion without incident, brightening and fading in a smooth, predictable manner. In this most likely scenario, nothing extraordinary occurs, and the comet continues its journey without drama. Yet this quiet possibility is the one that receives the least attention amid the swirling speculation. The real fascination during the blackout phase lies in observing how the narrative evolves in the absence of new data. Without fresh observations, the silence is filled with conjecture. Old images are recirculated and scrutinized. Amateur anomaly hunters dissect every pixel of pre-blackout data. And the mysterious connections, such as the supposed link to Quantico, are repeatedly revisited and reinterpreted. Prominent figures like the outspoken Harvard astronomer R.V. Loeb might even take to social media to stir the pot with provocative comments, fueling the speculation. As the weeks pass and we finally re-establish contact with 3I Atlas in December, the story will have inevitably grown in complexity. Layers of interpretation, inference, and sometimes misinformation piling up, regardless of how closely they mirror reality. Given this, my sincere advice is to set your expectations now. The blackout period is real, and the data gap is an unavoidable consequence of the orbital geometry itself. The Sun's position relative to the comet and Earth simply makes observation impossible at the most crucial moments. Whatever unfolds at perihelion, we will not have immediate clarity. Instead, we will be left with breadcrumbs, tentative clues from Mars orbiters, broad and coarse data from solar observatories, and a period of waiting. Early December marks the time when Earth-based telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, can once again pivot and direct their instruments toward the comet, provided it remains of interest. Meanwhile, ground observatories across the globe will resume tracking its path, and over the subsequent weeks, astronomers will piece together the puzzle of what actually happened during perihelion. If 3I Atlas emerges from perihelion still intact, and if subsequent observations reveal an increase in water vapor relative to carbon dioxide, consistent with models suggesting that heat has penetrated and unlocked deeper layers of ice, this would support the so-called thermal layer hypothesis. It implies that underlying ice, rich in water, was hidden beneath a crust of more volatile carbon dioxide, and heating during perihelion caused this ice to sublimate. Conversely, if the comet fragments, breaking apart into multiple pieces, or exhibit strong non-gravitational acceleration that cannot be explained by normal outgassing, the more exotic hypotheses will come back into focus. Perhaps the object is not purely natural after all, or some form of anomalous behavior is at work. But here's the sober reality. By the time we gather enough data to reach firm conclusions, the most dramatic moments, those defining the comet's behavior during perihelion, will have already slipped by unseen. Perihelion occurs in the shadows, in the dark, from an observational standpoint, simply because the Sun's position renders direct viewing impossible. That is an intrinsic feature of orbital geometry. The Sun doesn't bend to our observation schedule. After the blackout, if the comet unexpectedly brightens or if those mysterious anti-tail illusions reappear, tail structures that seem to point toward the Sun rather than away from it, anticipate the resurgence of. That's precisely why a time-stamped, geometry-corrected analysis holds such vital importance. Without proper context, an image is nothing more than a raw, unprocessed snapshot, akin to a snapshot of a shadow on a wall, lacking depth and meaning. During periods when observations are limited or the view is obstructed, patience becomes our greatest virtue. It's crucial to resist the temptation to leap into speculation simply because we're temporarily in the dark. Instead, we must wait for verified data, for metadata that confirms what we're seeing, and for cross-checks against the official channels that have the authority and rigor of scientific validation behind them. Most of what circulates during these information gaps, these moments when direct observation is hindered, is mere noise, misinterpretation, or conjecture, often amplified by the human tendency to fill silence with stories. The true signal, the reliable data, arrives later, deliberately, carefully, and slowly. But when it does, it's far more trustworthy. When we finally reacquire the object, in this case the third interstellar visitor designated 3I Atlas, and begin to gather fresh, high-quality data in December, we'll need a solid framework for interpretation. This framework must include well-defined hypotheses that are designed to be testable, predictions that can be verified or falsified, and a decision tree, a logical pathway that guides us from raw observation to meaningful conclusion without becoming mired in unproductive detail. It's about creating a scientific roadmap for navigating uncertainty, ensuring that every step is rooted in evidence and logical reasoning. To do this effectively, we should first lay out the range of possible explanations, from the most mundane to the most speculative, covering natural origins, exotic or artificial possibilities, hybrid scenarios, and even outright bonkers hypotheses. For each, we'll specify what kind of evidence would support or challenge these explanations, turning what might seem like idle speculation into rigorous, testable science. Let's begin with the most conservative baseline hypothesis: that 3I Atlas is a natural comet, driven by the volatile chemistry familiar to us from our solar system. But with a twist, its composition and behavior are shaped by conditions in another star system. This idea is rooted in the understanding that science advances by proposing explanations and then actively trying to find contradictions. You don't prove a hypothesis true, instead you look for evidence that could disprove it. The absence of such evidence keeps the hypothesis alive, while any conflicting data can prompt revisions or rejection. In this baseline scenario, the most straightforward explanation is that 3I Atlas formed in an interstellar environment where carbon dioxide ice was more prevalent than water ice. Perhaps its parent star had a different carbon-to-oxygen ratio than our Sun, resulting in a distinct chemical signature. Alternatively, it may have condensed in the colder outer regions of a protoplanetary disk, where CO2 would freeze out more readily than water. The high ratio of carbon dioxide to water isn't necessarily a sign of alien technology or extraordinary physics. Instead, it could be a direct fingerprint of its stellar birthplace, evidence of extraterrestrial chemistry. The key prediction here is that strong carbon dioxide emission bands will persist as the comet approaches perihelion and continue afterward. Water vapor should remain relatively subdued compared to CO2, although it might increase slightly after perihelion as solar warmth penetrates deeper layers of the nucleus, but it should never come to dominate the volatile emissions. Variability in outgassing, manifesting as episodic jets, could occur due to the patchy nature of the surface composition and the effects of the nucleus's rotation, factors that naturally produce irregular activity patterns. Furthermore, the non-gravitational accelerations observed in the comet's trajectory should be consistent in both magnitude and direction with the outgassing patterns. These accelerations should appear chaotic and lack a coherent or directed thrust, simply reflecting the random venting of gas and dust rather than any guiding mechanism. Such behavior aligns with our understanding of natural cometary physics. To falsify this hypothesis, we would look for signs that challenge these expectations. For example, if water suddenly becomes the dominant volatile without a plausible increase in solar heating, that would be suspicious. If the observed non-gravitational accelerations are significantly larger than what the measured gas emissions could produce, it suggests additional forces or processes at work. And if the signature of carbon dioxide vanishes entirely, replaced by some other and unexpected material, then we'd need to revisit and revise our model, possibly considering more complex internal structures or interactions. Moving to a more intricate explanation, consider the layered nucleus hypothesis with a thermal bottleneck. Here, the comet's composition remains naturally interstellar, but its internal structure is heterogeneous, comparable to a layered onion. The outer shell, a crust rich in carbon dioxide ice and embedded dust, acts as an insulator, shielding the water-rich interior from immediate solar heating. Beneath this insulating layer lies a reservoir of water ice that has yet to be exposed to sufficient warmth to sublimate. In this model, as the comet draws nearer to its perihelion, the closest point to the Sun, solar heating begins to penetrate its surface, setting off a process that unfolds gradually but inexorably. The heat doesn't instantly flood the entire nucleus. Instead, it propagates inward at a remarkably slow rate, akin to centimeters per hour, as heat conducts through the icy interior. This slow thermal wave travels through the layers of the comet's material, gradually awakening the volatiles trapped within. At this stage, the first and most readily observable response is the sublimation of carbon dioxide. Because CO2 resides in the outermost layers directly exposed to the sun's radiation, and because it sublimates at a comparatively lower temperature, it begins to vaporize first. This creates a visible coma dominated by CO2 gas, which is often reflected in the spectral signature we observe. Meanwhile, the water ice buried deeper beneath the surface remains frozen for now, shielded from the sun's intense heat by the overlying layers. As the thermal wave continues its slow march inward, the sublimation of water ice will eventually commence. When the heat reaches the deeper layers, the more stable and less volatile water molecules begin to vaporize, leading to an increase in water vapor detected in the comet's outgassing. This anticipated transition from CO2 dominance to a more balanced or water-rich composition forms a key prediction of the model. Specifically, before perihelion, the ratio of carbon dioxide to water, initially about 8:1, should decrease perhaps down to roughly 2 or even 1:1. Observations in December after perihelion should reveal stronger water emission bands reflecting this shift. Meanwhile, the comet's light curve, the variation in brightness, may also change as new regions of the surface become active and others develop crusts, effectively shutting down their outgassing. However, this model can be falsified if the expected chemical evolution simply does not occur. If, months after perihelion, the comet's chemistry remains static, with CO2 still overwhelmingly dominant and no significant increase in water vapor, the theory of a layered, thermally evolved nucleus would be called into question. Such an outcome would suggest that the comet's composition is more uniform than expected, or that some process is preventing the thermal wave from unlocking the subsurface water. In that case, the simplistic view of a natural CO2-rich comet would stand, or perhaps point toward a more exotic explanation altogether. Beyond the chemical predictions, there's a fascinating hypothesis addressing the comet's unconventional visual features. The large dust grains and the so-called anti-tail or sunward plumes. These anomalies, which include strange tail structures and bright spike-like features, can be explained without invoking any mysterious physics. Instead, they might result from the ejection of large dust particles, ranging from millimeters to centimeters in size, that do not respond strongly to solar radiation pressure. These hefty grains tend to follow the comet's orbital path more closely than smaller particles, which are pushed away rapidly by sunlight. As a result, from certain angles, the distribution of these grains creates the illusion of a tail or spike pointing toward the sun, an apparent sunward feature that is purely a matter of geometry and viewing perspective. The key prediction here is that these sunward features should appear and vanish as the relative positions of the Earth, the comet, and the Sun change after the blackout period. As the phase angle, the angle between the Sun, the comet, and the observer evolves, the morphology of these features should change in predictable ways. By modeling the dust trail in 3 dimensions and projecting it onto the sky at different times, Scientists can verify whether the observed structures align with the expectations of a ballistic dust distribution. Spectroscopic analysis of these features should reveal a dominance of dust continuum, reflected sunlight bouncing off the particles rather than molecular emission lines typical of gas. If, however, the features persist regardless of viewing geometry, or if their spectra show gas emissions instead of dust reflection, then the explanation based solely on geometry falls apart, and alternative causes must be considered. Pushing into less conventional territory, another intriguing hypothesis involves the presence of cryovolcanic pockets or chemically unusual regions within the nucleus. It's possible that the comet harbors subsurface cavities or fractures filled with highly pressurized volatiles, ices containing exotic compounds, that have remained trapped beneath the surface. When the thermal wave from the sun finally reaches these pockets, they could rupture explosively, releasing sudden plumes of gas with an unusual, perhaps even unexpected chemical signature. Such releases might involve trace species that have yet to be observed, including sulfur compounds, nitrogen-based molecules, or complex hydrocarbons, potential indicators of exotic chemistry or even biological precursors, although the latter remains speculative. These episodic outbursts would be characterized by transient spectral features, brief spikes in certain emission lines, signaling the sudden venting of previously hidden materials. If such events occur, they could dramatically alter the composition and appearance of the outgassing, providing clues about the internal heterogeneity. Predictions about the behavior and composition of the object become increasingly precise as observations continue. For instance, sporadic outbursts that align with new surface areas being exposed to sunlight could be identified through detailed time series spectroscopy. Such transient features, specific emission lines that suddenly appear over hours or days and then fade away, might also be asymmetric, giving rise to directional jets. These jets, if they exist, could cause measurable shifts in the object's orbit, providing clues about its activity. Importantly, the spectral signatures of these outbursts should be reproducible across multiple observations, not just a single anomalous detection, thereby allowing scientists to test hypotheses and falsify theories. If, however, the outbursts do not correlate with newly exposed surface areas, and if the chemistry appears mundane, lacking transient features in the spectra, then the need for complex internal pockets of volatile materials diminishes. Instead, the behavior could be entirely explained through standard sublimation processes occurring on a surface that is either homogeneous or patchy, without the need for embedded pockets or artificial structures. This leads us to the more speculative but intriguing notion of embedded ballast jets, an idea often linked to the hypothesis that the object might be artificially controlled. Imagine the nucleus contains jets that fire in a repeatable, patterned manner, always emerging from the same locations and synchronized with a specific rotation phase. Such a system would produce non-gravitational accelerations that are less random and more systematic, giving the appearance of controlled propulsion. However, this pattern wouldn't necessarily imply advanced technology. Instead, it could result from natural processes. The shape of the nucleus, its rotation dynamics, and the distribution of volatiles might naturally conspire to produce a quasi-stable jetting pattern that mimics control. With this hypothesis, predictions become testable. For example, if the jets are indeed controlled or at least appear to be, the non-gravitational acceleration should be phase-locked to the object's rotation period. Suppose the nucleus completes a full rotation every 14 hours, and the jets fire consistently at the same rotation phase. In that case, we would observe a coherent, repeating thrust pattern. The magnitude of this acceleration should align with the amount of gas being produced, adhering to the laws of momentum conservation, not exceeding what the outgassing can physically produce. The directionality, however, would seem unusually precise, hinting at some form of control. Furthermore, astrometric measurements should reveal orbit changes that are too regular, too neatly patterned, to be attributed to random outgassing. If, on the other hand, the jets are erratic, firing at random times in random directions with no phase locking, such a pattern would undermine the control hypothesis. In that case, the object would behave just like a typical comet, driven by natural sublimation and activity. Venturing further into the realm of speculation, some scientists consider the possibility that the object could be a hybrid, primarily a natural nucleus but modified with an artificial shell or interior structure. Picture a comet-like body that has been hollowed out or embedded with non-natural elements, perhaps an internal shell or a structure that's not of natural origin. The bulk composition might still appear comet-like because most of it is, indeed, ice and rock from space. Yet certain signals, exotic emissions or signatures not matching typical porosity or density, could suggest internal voids, metallic components, or engineered features. Radar reflections or cross-sections that imply the presence of internal cavities or metallic structures, or light curves with harmonic distortions and periodicities inconsistent with a simple rubble pile, could serve as indicators. Spectral signatures indicating manufactured compounds, industrial byproducts, or other anomalous elements would further support this hypothesis of artificial interior modification. If all measurements, spectroscopy, radar, light curves, are consistent with natural ice and rock, and if no anomalous spectral features or internal structures emerge from the data, then the simplest explanation remains that the object is a naturally occurring comet. In that case, the idea of a shell or interior structure would be falsified, reaffirming its natural origin. There is no evidence of interior modification. It is simply a natural comet. The hypothesis that suggests an artificial origin, one involving deliberate design and purpose, falls under what might be called the Vavilov territory. The trajectory of this object appears intentionally crafted. The planned flyby of Mars, the precise timing of perihelion, and the sequential encounters with multiple planets all seem too coordinated to be mere coincidence. This pattern prompts us to consider a provocative possibility. Perhaps 3I Atlas is not a comet at all, or perhaps it is a comet cloaking something else beneath its surface. One compelling idea is that it might be a probe, either actively controlled or following a pre-programmed route, sent by an intelligence seeking to study multiple planets during a single pass through our solar system. The most decisive indicator of this would be non-gravitational accelerations that cannot be accounted for by typical outgassing processes. If measurements reveal thrust forces that are unexpectedly large or directed in ways incompatible with any plausible jet configuration, that would serve as a definitive sign, your smoking gun. Alternatively, the detection of radio emissions, structured signals, or modulation patterns, any form of communication or telemetry, would strongly suggest an artificial origin. Further clues could come from anomalies in the light curve, periodic flashes, brightness variations with harmonic patterns that seem unnatural, or geometric occlusion effects that hint at a non-spherical, non-natural shape. Such features would be difficult to reconcile with a natural comet, especially if they exhibit signs of deliberate design. To falsify the artificial hypothesis, one would look for consistency with natural processes. If all observed accelerations align precisely with models of outgassing, if there are no detectable radio signals, and if the light curve behavior matches that of a typical rotating comet nucleus with patchy activity, then the simplest explanation is that it's a natural object. In that case, there's no need to invoke extraterrestrial technology, just a very unusual but natural comet. However, if the data shows systematic deviations, such as accelerations that break the laws of physics as we understand them, or spectral features that do not match any known molecular transitions, then the case for something exotic becomes stronger. These could include phenomena like interactions with unknown matter, effects from modified gravity, or radiation pressure anomalies that our current models cannot explain. The key to supporting such extraordinary claims lies in reproducibility. These anomalies would need to be observed consistently across multiple instruments and observation sites to rule out measurement errors or natural variability. Predictions that would challenge established physics include systematic residuals in astrometry that fail to correlate with outgassing models, brightness changes that defy conservation of energy or thermodynamics, or spectral signals that do not match any known molecules. Such anomalies would fundamentally undermine our current understanding of physics. Conversely, if all measurements, post-perihelion astrometry, spectroscopy, and radio observations, align neatly with natural models, then the object remains comfortably within the realm of the natural universe. The absence of radio signals detected by sensitive instruments such as the Very Large Array or the Allen Telescope Array would further rule out artificial transmissions. Similarly, if the chemistry of the object stays within the bounds of known cometary volatiles, without any signs of synthetic compounds or industrial signatures, it reinforces the idea that we are observing a natural phenomenon. The most important attitude here is a willingness to accept straightforward, boring answers when they fit the data. Even if 3I Atlas proves to be a chemically unusual but entirely natural comet, that discovery remains profoundly fascinating. It would provide new insights into the diversity of organic and inorganic chemistry in other stellar systems, and expand our understanding of comet formation and evolution beyond the familiar confines of our solar neighborhood. Such a conclusion would remind us that the universe is inherently strange and complex, without the need for artificial or alien explanations. It offers profound insights into how planets form around other stars, revealing the astonishing diversity of chemical environments within protoplanetary disks. Such data illuminate the intricate processes that govern the birth of planetary systems and allow us to compare our own solar system's characteristics with those of distant worlds. The beauty of this scientific pursuit is that it doesn't rely on the existence of extraterrestrial life to captivate our curiosity. The natural complexities and anomalies alone are enough to ignite wonder. Yet if the observations reveal inconsistencies, if anomalies persist under rigorous scrutiny, then our scientific journey demands that we follow these clues wherever they may lead, even if the destination is uncomfortable or challenges our current understanding. The upcoming moments are critical. The Mars flyby, a key event in this cosmic investigation, is happening right now. The perihelion, those closest points to the Sun, are less than a month away, and the post-blackout observation phase begins in December. Each of these windows in time constitutes a vital opportunity to refine, narrow, and test our hypotheses, systematically ruling out what is unlikely and focusing in on what could be true. So what should we be paying close attention to during this period? Let's begin with the event unfolding as you listen, the Mars encounter on October 3rd, 2025. At present, the interstellar object known as 3I Atlas is making its closest approach to Mars, passing within approximately 0.19 astronomical units, about 30 million kilometers, of the red planet. The European Space Agency's Mars orbiters, Mars Express and the ExoMars Trace Gas Orbiter, are actively engaged in a comprehensive observation campaign. This is it, the crucial moment. In the coming weeks, scientists will release data that could hold the key to understanding this object's true nature. The first and perhaps most revealing aspect to scrutinize is the spectral evolution of the comet's coma, the gaseous envelope surrounding its nucleus. Since this is fundamentally a chemistry story, the spectral data will tell us about the composition and behavior of the volatile materials being released. The James Webb Space Telescope's preprint from August provided a snapshot of the comet's composition at that time. It showed a dominance of carbon dioxide, with a CO2 to water ratio of roughly 8:1. Trace amounts of carbon monoxide and carbonyl sulfide were also detected. However, it's important to remember that this initial snapshot was captured when the comet was still farther from the Sun and less active, less heated, less outgassing. Now, as the comet draws closer to perihelion, its nearest approach to the Sun, the question arises, will its chemical signature change? If the layered nucleus hypothesis holds true, solar heating should begin to penetrate beneath the outer crust, which is rich in CO2. This could result in an increase in water vapor emission, decreasing the CO2 to water ratio from 8:1, down to perhaps 5:1 or even 3:1. Such a shift would be significant because it would indicate that water ice is indeed present within the nucleus, simply buried beneath a layer of CO2-rich material, and that thermal processing is unlocking this hidden reservoir. Conversely, if the ratio remains high or even increases during approach, it would support a simpler model, where the comet is not layered but rather a fundamentally CO2-rich object all the way through. This would suggest a different origin story, perhaps a comet formed in an environment where carbon dioxide ice was more abundant relative to water ice, reflecting a different stellar chemistry. Beyond the primary volatile, the trace species detected in the spectral data are equally important. Carbonyl sulfide, OCS, was observed in the JWST spectrum, raising questions about the sulfur chemistry within the comet. Will its abundance change as the comet warms? Are new molecules, such as sulfur dioxide, ammonia, or methane, appearing or disappearing? These chemical signatures are more than mere curiosities. They act as fingerprints of the conditions in the comet's birth environment, revealing whether it formed in a reducing or oxidizing setting. The presence of organic molecules, even simple ones like formaldehyde or methanol, would be particularly intriguing. While these do not directly imply life, they serve as fundamental building blocks, ingredients necessary for prebiotic chemistry, and can inform us about the chemical pathways active during the formation of these distant objects. Isotopic ratios, often considered the holy grail of cometary science, hold the potential to unlock the history of the comet's origin. The ratio of deuterium to hydrogen, D to H in water molecules, for instance, provides clues about the temperature and radiation environment in which the comet's ices were formed. Similarly, the ratio of carbon-vanadate to carbon-trinidate informs us about the stellar environment in which the carbonaceous material originated. In sum, as the comet approaches perihelion, scientists will be watching for changes in its spectral signature, shifts in volatile ratios, the appearance or disappearance of specific molecules, and isotopic variations. These measurements are crucial for distinguishing among different formation. If the instruments aboard the James Webb Space Telescope, JWST, possess the spectral resolution and sensitivity necessary to identify subtle isotopic variations within the comet's coma, such findings could be groundbreaking enough to merit publication in journals of the highest scientific caliber, such as Nature. Such a measurement would serve as a direct chemical fingerprint of the stellar environment in which the comet originally formed, an extraterrestrial signature encoded in its isotopic ratios, revealing insights into the chemical makeup of its birthplace star system. Beyond chemistry, the morphology of the dust tail and the effects of phase angle, namely the angle between the Sun, the comet, and the observer, are crucial observational parameters that can help unravel the physical nature of the comet's activity. As the Mars orbiters observe from varying geometries during the October 1st to 7th window, the phase angle will shift. This variation provides an opportunity to test the so-called anti-tail hypothesis, which posits that certain tail structures appearing sunward are merely optical illusions caused by viewing geometry. If the unusual tail features are indeed purely geometric effects, then their apparent orientation should change predictably as the viewing angle shifts. For example, dust that seems to be pointing toward the sun at one phase angle should appear more conventional or aligned with the expected orbital trajectory at another. Conversely, if these sunward features persist stubbornly across different viewing geometries, remaining unchanged regardless of phase angle, then simple dust dynamics models cannot sufficiently explain them. Such a scenario would imply the presence of more complex phenomena, such as jets with unusual directionality, particles with atypical scattering properties, or some other unanticipated physical process at play. The Omega instrument aboard Mars Express offers the capability to create detailed spatial maps of the coma. Should the comet exhibit localized jets, regions where gas and dust production are concentrated, Omega could potentially resolve these areas as brightness enhancements in specific directions. Detecting such localized activity would strongly suggest the presence of active regions on the nucleus, with others remaining relatively inactive, thereby supporting the patchy surface model. This detailed spatial information could reveal the heterogeneity of the nucleus's surface, providing key clues about its structure and activity. The measurement of the comet's non-gravitational acceleration offers a subtler yet arguably more critical line of inquiry. By combining precise astrometric data obtained prior to the Mars encounter with observations during and after the flyby, astronomers can fit the comet's orbit with remarkable accuracy. Any deviations from a purely gravitational trajectory, small residuals, may indicate the presence of thrust generated by asymmetric outgassing jets. The core question becomes whether these residuals align with the expected thrust based on observed gas emissions, particularly strong carbon dioxide venting. Calculating the expected thrust involves straightforward physics, primarily the principles of momentum conservation and the rocket equation. If the measured acceleration matches the predicted value derived from the observed outgassing, then the comet's behavior aligns well with standard cometary physics. However, if discrepancies arise, if the acceleration exceeds expectations or points in an unexpected direction, then questions about the nucleus's activity or even its nature are raised. The advantage of the Mars flyby phase is that it offers a long baseline of observational data collected over a short span, days rather than weeks, enabling a tightly constrained orbit determination. Multiple measurements of the comet's position during this period can reveal even minute deviations from expected trajectories. Should any anomalous acceleration be present, it would manifest clearly in the residuals, providing critical evidence about the dynamics at play. Additional observational data from other spacecraft could enrich this analysis. For instance, if the Mars Reconnaissance Orbiter, MRO, Mars Odyssey, or the Mars Atmosphere and Volatile Evolution, MAVEN orbiter contribute observations, though their involvement remains unconfirmed, these would add valuable independent lines of evidence. MAVEN's ultraviolet instruments could detect emissions from hydrogen or oxygen in the coma, which serve as tracers for water dissociation. If water vapor is present but not prominently visible in infrared spectra from TGO, UV observations could still reveal its presence. Similarly, MRO's high-resolution imaging could independently confirm the comet's position and motion, providing another means to detect subtle orbit changes. Altogether, these combined data streams, spectral, spatial, and astrometric, would enable a nuanced understanding of the comet's activity, composition, and dynamics, helping to distinguish natural phenomena from more exotic possibilities. The infrared instruments aboard the Mars Odyssey spacecraft could play a vital role in advancing our understanding of the comet's surface and internal properties. By measuring the temperature of the dust and dust-covered nucleus, these observations could help constrain critical parameters such as grain sizes and surface reflectivity, known as albedo. The more independent measurements we gather from different instruments and vantage points, the less vulnerable we are to potential misinterpretations caused by instrumental artifacts or calibration errors. This process of cross-validation acts as the immune system of scientific inquiry, ensuring that our conclusions are robust and credible. One particularly intriguing, albeit speculative, possibility involves the presence of directional jets emanating from the comet. If during the encounter some jets are firing toward or away from Mars, the geometric perspective from the Martian orbit could provide a clearer, more detailed view of their structure than what Earth-based observations might offer. Typically, jets on comets are thought to be closely tied to solar heating, which causes sublimation of volatiles on the sun-facing side of the nucleus. As a result, jets generally point sunward or anti-sunward, following the pattern of sublimation driven by solar energy as the comet rotates. However, if there were any asymmetry in the activity, say jets pointing unexpectedly toward Mars or in unusual directions, it would appear quite strange from our viewpoint. Such a scenario wouldn't imply that the comet is intentionally targeting the planet, as comets do not possess the capacity for aim or purpose. Yet observing such directional jetting would be noteworthy and worthy of closer investigation. More likely, any jets detected would align with the sublimation pattern, consistently oriented toward the sun or away from it, as dictated by the nucleus's rotation and localized volatile distribution. The importance of a null result, where no unusual activity or anomalies are observed, should not be underestimated. If the Mars observations reveal a past that appears entirely routine, with compositions and dust behaviors matching those predicted by the James Webb Space Telescope's data, that outcome is scientifically valuable in its own right. A boring pass effectively narrows down the range of hypotheses, ruling out more exotic or anomalous behaviors, and confirming that the comet is behaving as expected within the known framework of cometary physics. Establishing this baseline is crucial because science isn't solely about discovering anomalies. It's about understanding what normal looks like so we can recognize and interpret the truly extraordinary when it occurs. It's also essential to acknowledge that there will be a delay between data collection and public dissemination. Calibration pipelines, especially for spectroscopic data, are complex processes that require meticulous processing. Raw data must undergo wavelength calibration, background subtraction, correction for instrument response, and comparison against known reference spectra, all of which can take days to several weeks. Additionally, internal review procedures within the mission teams, coordination with agencies like NASA and the European Space Agency, and possibly peer review processes for scientific publishing further extend this timeline. Realistically, the first fully calibrated and analyzed data from the Mars observations might not be available until late October or early November. Prior to that, preliminary results, perhaps from conference presentations or informal updates on mission blogs, may leak or be shared. It's important not to interpret these delays as signs of suppression or concealment. Instead, they reflect the rigorous, careful pace of scientific validation. Scientific integrity demands patience. If one seeks speed over accuracy, one risks accepting sloppy, unreliable conclusions. True science progresses at its own deliberate tempo, and the upcoming period will be no exception. As the Mars observation window narrows, it is expected to close around October 7th, after which the comet continues its inward trajectory toward perihelion, scheduled for the 30th of October. Beyond that point, Earth-based assets will lose sight of the object, and our direct observational window will effectively come to an end. Solar observatories in space might capture fleeting glimpses, but the primary focus will shift to waiting until December, when the comet re-emerges into view from Earth. Before we delve into what awaits after the blackout, it's crucial to recognize that the most dramatic and potentially revealing phase of 3I Atlas's journey occurs during this period of limited observation. An interval that will test our patience but also define the boundaries of our understanding. The moment of perihelion, the closest approach of a comet to the Sun, is often described as its ultimate test, its crucible, its fiery furnace. It is the point in the journey where everything comes to a head, where the comet either withstands the intense solar heat, disintegrates into a cloud of debris, or transforms into something entirely different. This is the core event, the decisive chapter in the comet's story, and it unfolds on October the 30th, 2025, a date that marks the perihelion of the enigmatic interstellar visitor, 3I Atlas. At approximately 1.4 astronomical units from the Sun, around 210 million kilometers, this distance situates the comet well inside Mars's orbit but comfortably outside Earth's. It's not a sun grazer by any stretch, not skimming the solar surface, but it's close enough that the Sun's heat reaches a crescendo for 3I Atlas during its entire voyage through the inner solar system. For a comet, this is the moment of truth, the point at which the internal and external forces at play reach their peak, and the comet's fate is sealed. Over the preceding weeks and months, the comet's volatile components, substances like carbon dioxide, water ice, and other gases, have been gradually warming, creeping ever closer to their sublimation points, the temperatures at which they transition directly from solid to gas. Meanwhile, subsurface layers of ice and dust have been slowly inching toward destabilization, building internal stresses as the side facing the Sun bakes and the opposite side remains frozen in shadow. The structural integrity of the comet has been under constant strain, and everything is now converging at this critical juncture. Yet paradoxically, much of this dramatic activity will happen out of our direct view. As 3I Atlas approaches perihelion, it will be enveloped in the intense glare of the Sun, rendering Earth-based telescopes virtually blind. The solar brightness will drown out any attempts at observation, forcing us to infer what occurs during this pivotal phase from observations made before and after the event. This period is fraught with uncertainty, and the potential scenarios are both fascinating and vital to understand. Let's consider the possible outcomes, their signatures, and how we might distinguish among them. The first scenario is the worst case, a catastrophic disintegration. This is the cautionary tale that haunts every perihelion prediction. The year was 2013, and scientists heralded Comet Ison as the comet of the century, expecting it to blaze brightly as it ventured within less than 2 million kilometers of the Sun at a perihelion distance of just 0.0 Odin AU. Instead, it disintegrated during its perihelion passage, torn apart by tidal forces, thermal stresses, or perhaps simply its own fragile structure. What remained was a faint fading cloud of dust, a remnant of what once was a coherent nucleus now lost to the void. Could 3I Atlas meet the same fate? While the distance is much safer, about 1.4 AU compared to Ison's perilous proximity, thermal stress still poses a real threat. If the nucleus is a loosely held together rubble pile composed of ice and rock loosely bound by gravity and weak structural cohesion, the sublimation of internal ice could cause it to fall apart. The signatures of such an event would be unmistakable once we regain the ability to observe again, likely in December. Instead of a sharp, bright point, a well-defined coma, we would see a diffuse, sprawling cloud of debris. The brightness would be significantly diminished, and astrometric measurements would become erratic, with the data fitting a debris field rather than a single solid nucleus. Spectroscopic signals might reveal unusual dust-to-gas ratios, with excess dust indicating pulverization of the nucleus. If disintegration occurs, it offers a sobering lesson. We would learn that 3I Atlas was a fragile interstellar visitor, perhaps a loosely bound conglomerate of ice and rock that had survived its long journey through the cosmos only to succumb under the sun's relentless heat. While we would lose the chance to study its long-term behavior, the debris cloud itself would provide valuable clues about its composition and structural integrity, enriching our understanding of interstellar objects and their internal architectures. On the other hand, there is the more optimistic possibility: graceful survival. This scenario mirrors the fate of Comet Lovejoy, C2011W3, a sun grazer that survived perihelion within a mere 0.006 AU of the Sun. Lovejoy endured the intense heat and gravitational stresses, emerging battered but intact, still outgassing vigorously as it receded into space. Its nucleus remained cohesive, and it continued its journey beyond perihelion, providing a rare glimpse into the resilience of certain cometary structures. For 3I Atlas, a similar outcome would mean that despite the extreme conditions, the nucleus persists as a well-defined certainly. Here's a deeply refined, expanded, and polished version of the provided text, crafted to flow smoothly and present a clear, compelling narrative. When the comet reaches perihelion, its closest approach to the Sun at approximately 1.4 astronomical units, the environment it faces is significantly less severe than that encountered by comets that venture much closer, such as the famous sun grazers. For those, the Sun's corona, where temperatures soar into the millions of degrees, poses a brutal challenge, often resulting in disintegration or dramatic alteration. Yet some comets, like the historic Comet Lovejoy, have demonstrated remarkable resilience, emerging from such fiery encounters battered but still intact, outgassing furiously but maintaining their structural coherence. During perihelion, Lovejoy's brightness soared, and though it eventually faded as it receded into the depths of space, it did so with a clear sense of resilience. In contrast, 3I Atlas is not facing such an extreme environment. Its perihelion distance means it should, under normal circumstances, be expected to survive the passage without catastrophic failure. The hallmark of a successful perihelion for a comet in this context is a smooth, steadily varying light curve, meaning the brightness should increase gradually as it approaches the Sun, peak at perihelion, and then decrease gradually as it moves away. Post-blackout observations conducted in December suggest that 3I Atlas has indeed come through this critical phase in good health. A well-defined coma with the core still visible, what astronomers call central condensation, and spectra indicating an evolved chemical composition, yet nothing to suggest imminent disintegration or structural collapse. Furthermore, the data shows that the comet's non-gravitational accelerations, tiny deviations in its trajectory, are consistent with what would be expected if it were venting gases but without exhibiting signs of fragmentation or sudden dramatic changes in activity. These subtle shifts align with natural outgassing processes and do not point to an unstable or breaking nucleus. Such an outcome might seem mundane, perhaps even dull from a narrative perspective, but in science, simplicity often signifies correctness. When a comet like 3I Atlas survives perihelion intact, it opens the door to extended observation windows. Months of follow-up as it journeys outward past Venus, Earth, and Jupiter. During this outbound phase, scientists will carefully monitor how the comet's chemistry evolves. Will water eventually become the dominant volatile, overtaking carbon dioxide? Will the episodic jets, those sporadic outbursts of activity, settle into a steady, predictable pattern, or will they continue to flicker unpredictably? The answers to these questions hinge on the evolution of the comet's internal structure and surface processes, making the chemistry changes the key predictions that can be tested through continued observation. If the layered nucleus model is accurate, that is, if the comet's interior is stratified with buried layers of water ice sealed beneath a crust of carbon dioxide-rich ice, then, after perihelion, we should see signs of significant change. The thermal wave generated by the sun's heating should have penetrated deep enough to unlock these hidden reservoirs of water. Consequently, the ratio of carbon dioxide to water in the comet's coma should drop markedly. The high initial ratio of about 8 parts carbon dioxide to 1 part water should decline toward a more typical equilibrium, possibly around 2 to 1 or even closer to a 1 to 1 ratio. Such a shift would be a clear indicator that the thermal wave has reached these buried water-rich layers, confirming the layered structure hypothesis and revealing the thermal evolution of the nucleus. However, if, despite the heating, the carbon dioxide remains the dominant volatile, if its relative abundance persists even after the peak heating phase, then we face a different conclusion. The comet might be inherently rich in carbon dioxide throughout its interior, with no hidden layers or stratified zones. Instead, we'd be dealing with a fundamentally unusual, perhaps even exotic composition, an object that defies conventional models of cometary behavior, possibly originating from a different stellar environment. Beyond the chemical evolution, there exists the possibility of dramatic explosive events, outbursts, that can dramatically alter the comet's appearance and behavior. Some comets, such as 17P Holmes and 2007, have exhibited sudden explosive brightening by factors of 1,000,000 within a single day, caught entirely unawares. Such outbursts are often attributed to the sudden exposure or venting of subsurface pockets of volatiles, or structural collapses of the nucleus that unleash a torrent of gas and dust. In these cases, the comet's brightness surges unexpectedly and the coma expands rapidly, becoming significantly larger and more active than predicted. If 3I Atlas experiences a major outburst at perihelion, the first telltale signs will likely come from solar observatories like SOHO or Stereo, which are designed to monitor the sun's corona and the space around it. They may record a sudden surge in brightness, indicating an explosive release of volatiles. During the perihelion phase, these solar observatories will serve as our sole direct real-time vantage points for monitoring the comet, specifically through instruments like SOHO's LASCO coronagraphs. These devices function by employing occulting disks that effectively block out the sun's intense photosphere, allowing us to capture the faint glow of the surrounding corona and any passing objects within it. Should 3I Atlas traverse the field of view of these instruments, it would manifest simply as a point of light or perhaps a streak, an indication of its movement against the solar background. Similarly, the Solar Terrestrial Relations Observatory, or STEREO, with its core instruments, provides a different perspective from vantage points positioned elsewhere in space. While STEREO's instruments lack the capability for detailed spectroscopy, meaning they cannot directly analyze the chemical composition of the object, they are invaluable for tracking brightness changes over time. They can tell us whether the comet appears to grow brighter or dimmer, whether it maintains a compact, well-defined form, or if it begins to spread out and fragment. These observations are far from trivial. They form the crucial baseline data that distinguish an intact, potentially oversized and active comet from debris or disintegrating fragments. This information sets the critical tone for subsequent observations, especially during the upcoming reacquisition in December. When the comet reappears after perihelion, our expectations hinge upon these early indicators: a healthy, cohesive nucleus or a scattered, diffuse cloud of debris. The importance of this initial assessment cannot be overstated, as it frames the entire narrative of the comet's post-perihelion evolution. Now, considering the physics involved, the stakes are higher than they might initially seem. At approximately 1.4 astronomical units from the Sun, the energy flux, meaning the solar power received per square meter, is roughly 500 watts. To place this into perspective, Earth at 1 astronomical unit receives about 1,368 watts per square meter. Although this is less intense, it remains a significant amount of energy for a body that has been in deep freeze for millions of years. This marks the warmest environment the comet has experienced since its departure from its original star system. It's important to understand that heat penetration into the comet's interior is a slow process. Ice, being a poor conductor of heat, resists rapid temperature changes. The thermal skin depth, the distance heat can penetrate within a given time, is typically measured in centimeters to meters for cometary ice. As a result, the surface heats up quickly, causing sublimation or the formation of crusts of refractory dust that may temporarily insulate the interior. Beneath this crust, the temperature gradient remains steep. The deep interior ice remains cold for days or even weeks, even as the surface radiates heat away. This thermal lag gives rise to delayed effects. For example, water vapor release, signs of activity, may not peak until after perihelion, once the thermal wave has had enough time to reach the buried water-rich layers. Consequently, the maximum brightness or activity level might not coincide precisely with the point of closest approach to the Sun. Instead, a phenomenon known as hysteresis, an inherent lag in the system, causes the comet to brighten gradually as it approaches perihelion, and then fades smoothly afterward, consistent with classical thermal physics. However, if the comet's brightness spikes suddenly, drops abruptly, or exhibits discontinuities in the light curve, it signals that more complex structural or dynamic processes are at play. These could include fragmentation events, explosive outbursts, or sudden rotational changes, all of which are testable hypotheses. In the case of a disruption, post-blackout observations would reveal a faint, diffuse emission, lacking a clear central nucleus with an orbit that becomes increasingly uncertain or impossible to fit with standard models. Spectroscopic data would be dominated by dust continuum, the reflected sunlight and dust scattering, showing minimal gas signatures. If instead the comet survives perihelion intact, we would expect to see a stable, compact coma with a clearly defined central condensation. Spectra would be gas-rich, with chemical compositions indicating evolution from pre-perihelion conditions. The brightness would follow a smooth, predictable curve, and measurements of non-gravitational accelerations, tiny deviations from purely gravitational trajectories, would align with the outgassing activity expected from a healthy nucleus. In an outburst scenario, the comet's brightness would be significantly higher than predicted, with a large active coma and potentially new spectral features indicating the excavation of deep, previously hidden material. Non-gravitational accelerations might be temporarily enhanced, reflecting intense episodic jet activity. Finally, an exotic or anomalous scenario involves brightness changes that violate energy conservation principles, spectral features that do not match any known volatiles, or non-gravitational accelerations incompatible with plausible outgassing models. Such anomalies would raise questions about the comet's natural origin, potentially hinting at unusual physics or even artificial influences. In essence, these observational clues during perihelion. In the grand tapestry of scientific discovery, one truth remains unassailable. The universe refuses to adhere to our human schedules. The reality of communication today is that we must accept a fundamental limitation. We will not truly grasp which scenario has unfolded until many weeks after the event itself. Early hints might emerge from the data gathered by solar observatories like SOHO and Stereo as soon as early November, offering tentative glimpses of what transpired. Meanwhile, assets orbiting Mars could provide crucial contextual observations, but the complete picture, The one that truly clarifies the story will only come into focus in December, when Earth-based telescopes can once again reorient themselves, aim their lenses, and begin collecting photons from the distant scene. This delayed revelation embodies both the frustration and the fascination intrinsic to the craft of astronomy. It is a discipline rooted in patience, understanding that the universe's most vital moments often occur when our observational reach is temporarily severed. We reconstruct what happened through echoes and shadows, comparing data from before and after the critical event, building models that either fit the evidence or fall short. If the object known as 3I Atlas emerges from perihelion unscathed, intact, then the next phase, the outbound journey, becomes our testing ground. It's here that hypotheses will be validated or refuted, where the long game of understanding begins to reveal its secrets. As it moves beyond perihelion, the trajectory will carry it past the planetary neighbors, Venus, then Earth, and finally Jupiter, each encounter presenting new opportunities for coordinated observation campaigns. These moments are precious for refining our models of its orbit, for scrutinizing how its chemistry evolves as it cools and responds to the diminishing solar heat. It is in this phase that the true depth of scientific inquiry unfolds, where patience and persistence will determine how much we ultimately learn. This journey, however, isn't just about the physical path of the object. It also exposes the underlying narrative web woven around it, what I term the story bias, the gaps filled with silence, speculation, and bias that color our perception. To truly understand the significance of 3I Atlas, we must step back from the data and consider the stories we tell ourselves, because stories shape what we believe and how we respond. On one side, there are the established institutions, the space agencies like NASA and ESA, the broader astronomy community. Their approach is measured, deliberate, rooted in facts and cautious interpretation. Their communications are often in the form of detailed blog posts about Hubble's observations, preprints on repositories like Archive detailing spectroscopy results, and frequently asked questions pages that elucidate orbital mechanics. Their press releases read like technical documents, precise, vetted, and intentionally slow, reflecting a culture of error prevention and scientific rigor. This is the traditional authoritative style of science communication, built on meticulous peer review and cautious language. Contrasting this, there exists a vibrant landscape of alternative narratives, stories crafted and shared rapidly across social media platforms. Here, claims surface suggesting that NASA or other agencies are hiding vital information, that the object represents something extraordinary, possibly an alien probe, and that powerful forces are deliberately concealing the truth. These stories are often accompanied by ominous music, sensational titles like, "Is this a probe or an alien craft?" and Reddit threads linking the object to secret military projects, Quantico, or decades-old conspiracy theories about government suppression of alien contact. They thrive on immediacy, emotion, and shareability, often bypassing scientific peer review or cautious language, instead offering clear villains and hidden truths to be uncovered. Between these extremes lies a space of legitimate scientific speculation, where researchers like Avi Loeb openly entertain exotic hypotheses and amateur astronomers share raw observations that may seem peculiar but warrant consideration. Science communicators endeavor to explain the data honestly while acknowledging its weirdness, trying to strike a balance between skepticism and openness. This middle ground is where the richest conversations happen, where curiosity is fostered, but it is also the most difficult space to occupy. It pulls us in two directions, toward institutional caution, which values accuracy and consensus, and toward sensationalism, which seeks engagement and viral attention. Navigating this terrain requires discipline, humility, and an awareness of the narratives we are constructing. Because in the age of instant media, stories often take on lives of their own, independent of the data. Understanding these narrative dynamics is crucial. They influence public trust, shape funding priorities, and determine how future discoveries, be they interstellar objects or unidentified aerial phenomena, are perceived and acted upon. Recognizing that stories are powerful, that they can distort or clarify, is the first step toward responsible engagement. As we await more definitive data, it's essential to remember that the universe's truths are often revealed gradually in shadows and echoes, through patience and rigorous analysis. Only then can we hope to distinguish genuine anomalies from the noise of speculation, and truly understand what lies beyond the horizon of our current knowledge. The pervasive asymmetry within our media landscape fundamentally shapes how stories spread, and what ultimately captures public attention. Sensational narratives have an uncanny ability to go viral, while more measured, nuanced analysis struggles to gain traction. For instance, when NASA detects an unusual but undoubtedly natural comet, it garners only a few hundred clicks online. In stark contrast, if whispers emerge about an alien probe nearing Mars, an event that would be nothing short of extraordinary, the silence from NASA itself, despite its importance, is met with a flood of attention, reaching hundreds of thousands of viewers. The reason for this discrepancy lies in how the digital environment rewards certain qualities: novelty, certainty, and emotional impact. Clear, cautious scientific explanations, which tend to be complex and nuanced, rarely deliver these immediate satisfactions. Instead, they are overshadowed by bold claims that promise mystery and drama. What then is the outcome? The sensational stories, however unsubstantiated or misleading, spread more rapidly and extensively than the corrective efforts that aim to clarify or debunk them. By the time a credible astronomer or scientist publishes a thorough rebuttal, explaining precisely why the so-called sunward tale is merely an illusion, a narrative constructed from misinterpreted data, the original viral post has often been shared tens of thousands of times. That initial wave of attention cannot simply be erased. The bell cannot be unrung. The correction, no matter how accurate, reaches only a fraction of the audience that initially encountered the sensational claim. This phenomenon isn't new. It has existed since the days of the printing press, long before the age of radio and television. However, social media amplifies this effect exponentially, accelerating the spread of misinformation so that corrections frequently arrive too late to change minds effectively. The narrative, once established, begins to feed itself, layering inference upon inference, making it increasingly difficult to disentangle fact from fiction as time passes. A prime example of this dynamic is the case of Quantico. Despite there being no official or public linkage between the military gathering at Quantico in late September and the passing of the interstellar object known as 3I Atlas, the coincidence in timing fuels speculation. Human brains are pattern-matching machines wired to find connections where none exist. When two seemingly unrelated events happen concurrently, such as a high-level military meeting and a celestial object approaching Mars, our minds instinctively infer causation. They must be connected. This is not a matter of logical deduction, but of narrative construction. The pattern appears so neat. Military officials convene, and shortly after, an unusual object nears Mars, that it feels compelling, even inevitable. Once this association is formed, every piece of ambiguous information tends to reinforce it. Questions like, why won't the military disclose what the meeting was about? Or, why is NASA so silent about 3I Atlas? Are interpreted as evidence of a cover-up. Each absence of clear information becomes a strand in the web of a broader story, feeding suspicion and speculation. Throughout this discussion, my goal has been to maintain what I call responsible framing. acknowledging events as they are without jumping to conclusions about their interconnectedness. Yes, Quantico occurred. Yes, 3I Atlas is passing through the solar system. But currently there is no evidence linking the two. If future reports or investigations establish a connection, then we will revise our understanding accordingly. Until that point, these are separate stories unfolding side by side. Yet this disciplined approach is far more challenging than succumbing to the sensational narrative. It demands intellectual discipline, patience, and a willingness to accept uncertainty. Traits that most people find uncomfortable in an era of instant gratification and click-driven content. The allure of straightforward, dramatic answers. It's an alien probe, or NASA is hiding something, is strong because such stories fulfill our craving for certainty and emotional engagement. The stories that have shaped public discourse, such as debates about the hypothetical alien origins of objects like UFOs or UAPs, are often built on this template. For example, the case of UFO and UAP reports with their mysterious videos and ambiguous sightings primes the public to interpret unexplained phenomena as signs of extraterrestrial technology. Similarly, the case of Oumuamua, with its elongated shape and observed non-gravitational acceleration, became a template, a strange object with an unusual shape, exhibiting behavior that defies straightforward explanation and accompanied by hypotheses of alien technology, namely an alien light sail proposed by Avi Loeb. This pattern building creates a mental scaffold that makes it easier for the public and media to jump from unusual to probably alien without sufficient evidence. Once these templates are in place, subsequent events, such as the passing of 3I Atlas, are interpreted through the same lens, often amplifying exotic possibilities even when the data remains consistent with natural phenomena. In summary, the core issue is that the media ecosystem biases. When a new interstellar object ventures into our solar system, many instinctively attempt to apply a familiar mental template, an underlying map, onto it. They look for the same familiar signs, an unusual shape, an anomalous trajectory, or strange behavior. But here's the critical point. We don't actually know the true shape of these objects. There's a tendency to assume that certain features, like an unusual form, are present simply because they fit a preconceived narrative. Similarly, when it comes to acceleration, the human mind expects to see signs of non-gravitational forces. Again, a familiar pattern. But the truth is, we haven't conclusively measured that yet. Our assumptions often outpace our data. Institutional silence is another pattern that gets invoked. Many interpret a lack of immediate official commentary as evidence of concealment or suppression. But in reality, institutions aren't necessarily silent in the way we imagine. They're just not broadcasting at the levels that capture public imagination or satisfy sensational narratives. Their caution stems from a desire to avoid prematurely overstating findings, mistakes that could damage credibility, especially after past episodes where early claims proved false or misleading. This cautious approach is rooted in institutional memory, which teaches the value of patience and verification. However, this prudence can sometimes appear as deliberate suppression when, in fact, it's just a matter of measured science. Meanwhile, content creators, YouTubers, podcasters, bloggers operate within a different incentive structure. Their success depends on attracting attention through novelty and certainty. A video titled "Comet Mystery Deepens" tends to garner more engagement than one discussing unusual but normal comet chemistry. The algorithms that govern digital platforms prioritize emotional intensity and engagement, not accuracy or nuance. As a result, the incentive for creators is often at odds with the cautious restraint of scientific institutions. This divergence creates a landscape where the public is caught in the middle, navigating between institutional caution and the sensationalism driven by social media. Without clear guidance on whom to trust, people are vulnerable to cognitive traps. These include cherry-picking, highlighting observations that support a preferred narrative while ignoring contradictory evidence, and argument from ignorance, assuming that if something hasn't been proven false, it might be true. For instance, if someone claims that NASA hasn't definitively ruled out an artificial origin, that does not automatically mean the object is artificial. It only indicates a lack of disproof, which is not the same as proof. Another common fallacy is the conjunction fallacy. The mistaken belief that specific detailed scenarios, such as an alien probe designed to study multiple planets, are more probable than more general natural explanations like a comet with unusual chemistry. The narrative appeal of the former often makes it seem more compelling, but probability doesn't work that way. Just because a story is more satisfying doesn't mean it's more likely. Confirmation bias further complicates our understanding. This is the tendency to interpret ambiguous evidence as supporting pre-existing beliefs. If someone already suspects cover-up or alien technology, they are more likely to see signs, real or not, that confirm that suspicion. Conversely, skeptics may dismiss anomalies as natural variations regardless of how puzzling they appear. Recognizing these biases is crucial for maintaining scientific objectivity and avoiding being led astray by our own mental shortcuts. In essence, the challenge is to distinguish genuine scientific signals from noise, to see beyond the patterns our minds are predisposed to recognize. This requires disciplined analysis, an awareness of cognitive traps, an understanding of the limitations of current data, and a cautious approach to interpretation. Only then can we move toward a clearer picture of what these mysterious objects truly are, whether natural or something more exotic. If you already hold the belief that NASA tends to hide or suppress information, then their cautious, measured manner of communication only reinforces that suspicion. Conversely, if your perspective is that comets are simply natural celestial objects, then this same restrained style appears as responsible scientific prudence. The reality is that the evidence is identical. The difference lies in the interpretive lens shaped by prior beliefs. To navigate this complex terrain responsibly, a spirit of productive skepticism is essential, one that combines rigorous tools and disciplined thinking. How can you remain open to discovering authentic anomalies without falling prey to every grandiose, unsubstantiated claim? The key begins with demanding provenance. Whenever someone shares an image or asserts a claim, ask, where did this originate? Which instrument captured it? What are the exact timestamps, the viewing geometry, and the calibration details? If these critical details are absent or vague, exercise caution and skepticism. Moreover, prioritize multiple epochs of data over isolated spectacular frames. A single dramatic image might be an artifact, an error introduced during processing, or a misidentification altogether. However, if the same unusual feature appears consistently across multiple observations, especially from different instruments and observatories, it becomes far more likely to be genuine. Cross-validation is the scientific safeguard against false positives. For instance, if 3i Atlas shows an anomaly, then do multiple independent observatories see it? Do spectroscopy results from the James Webb Space Telescope match those obtained from ground-based instruments? Such cross-checking helps eliminate artifacts and errors, anchoring interpretations in verifiable data. Follow the guidance of experts. Trust but verify. Yet avoid blind worship. For example, Avi Loeb, a distinguished Harvard astronomer, is a credible scientist, but he also represents a contrarian voice that challenges mainstream consensus. His hypotheses are worth considering, but it's essential to distinguish between ideas that are part of the scientific dialogue and those that are speculative or not yet widely accepted. Look for falsifiable predictions, testable hypotheses that can be confirmed or refuted by evidence. For example, claiming that 3-eye atlas is artificial is currently not falsifiable because the evidence isn't definitive enough. Proponents can always argue that the evidence isn't in yet. However, predictions such as detecting radio emissions indicative of intelligent origin or observing non-gravitational accelerations inconsistent with natural outgassing are falsifiable. These are measurable, testable phenomena that can either strengthen or weaken the hypothesis. The role of contrarians such as Avi Loeb is valuable. They serve as a check on complacency, compelling the scientific community to justify why certain exotic hypotheses are rejected. Their willingness to question prevailing assumptions pushes the boundaries of inquiry and fosters critical examination. That said, there's a delicate line where healthy skepticism turns into motivated reasoning, where a researcher clings to a pet theory despite mounting contrary evidence. The most responsible approach is to keep hypotheses separate from headlines. For instance, Loeb's suggestion that 1-eye Oumuamua might be an artificial light sail is an intriguing scientific possibility deserving investigation. But framing it as aliens visited is sensationalist and misleading. Similarly, the hypothesis that 3-eye atlas exhibits non-natural behaviors is worth testing. The claim that it is an alien probe targeting Mars is not supported by current evidence and remains purely speculative. In the end, the difference between scientific inquiry and sensationalism hinges on maintaining integrity in how hypotheses are presented. Scientific hypotheses should be tentative based on limited data and open to falsification. Headlines, on the other hand, tend to simplify or exaggerate, often blurring the line between what is known and what is conjectured. The key to responsible skepticism is to focus on the evidence, demand transparency, and recognize the limits of current understanding. Be wary of arguments from ignorance, assuming that because something hasn't been proven false, it must be true. Instead, rely on falsifiable predictions. If those predictions fail, the hypothesis must be reconsidered or discarded. Contrarians like Avi Loeb are a vital part of the scientific ecosystem. They challenge assumptions, encourage rigorous testing, and prevent complacency. But it's equally important to distinguish between hypotheses that are testable and claims that are not. Sensationalist headlines claiming aliens visited are not only irresponsible but also undermine public trust in science. Ultimately, scientific progress depends on a balanced approach, questioning boldly but also adhering to strict standards of evidence and clarity. When evaluating extraordinary claims, ask for provenance, seek independent confirmation, and remember that the best science is often the most boring, obtaining robust, reproducible data that can stand the test of scrutiny. Only through disciplined inquiry can we truly separate genuine anomalies from noise and arrive at a clearer understanding of what lies beyond our current knowledge. Narrative stewardship extends far beyond the confines of this singular object. Why is it so vital to engage in this meta-level analysis? Because the stories we craft about phenomena like the interstellar visitor directly influence how the public perceives science, how funding is allocated, and ultimately how future extraordinary objects will be received and studied. If in the end, 3-eye atlas is confirmed to be a perfectly natural comet, and all the surrounding speculation turns out to be mere noise, some individuals will feel disillusioned or even betrayed. They might become less inclined to trust official announcements or to engage with subsequent discoveries, primed to see alarmist claims or crying wolf. Conversely, if we approach these phenomena with responsible curiosity, speculating openly but cautiously, demanding substantive evidence, and updating our understanding as new data emerges, we lay the groundwork for a more resilient and nuanced model of how humanity handles the unknown. This approach fosters a culture where questioning what if is not taboo, but a disciplined exercise. It's about encouraging curiosity without leaping to conclusions, understanding that uncertainty is a natural and valuable part of scientific exploration. It's about recognizing that institutions communicate in their own cautious, methodical ways, not out of secrecy, but because science demands rigor and verification. Exotic hypotheses, no matter how alluring, must earn their place within the framework of evidence, not vibes or assumptions. In practical terms, this means knowing where to look and what to trust. It involves following official channels like the Minor Planet Circulars for astrometry updates, consulting JPL Horizons for the latest orbital data, and reviewing preprints on repositories like ARXIV, particularly those authored by the mission teams themselves. It requires paying attention to official statements from agencies like ESA and NASA, which, although slow, are vetted and grounded in peer-reviewed science. Listening to credentialed astronomers who communicate openly is essential, but always with a critical eye, distinguishing between expert consensus and personal speculation. Equally important is exercising skepticism toward unverified leaks, uncontextualized screenshots, and claims that lack instrument details or timestamps. Dramatic narratives that seem too neat or too perfect often hide the messiness of reality. Science is inherently uncertain. It's a process of gradual refinement, not instant revelation. If someone is offering certainty without evidence, they're selling a story, not science. Remember, even the most bizarre natural comet we've ever encountered remains astonishing in its complexity and beauty. No aliens required to make the universe fascinating. So what should you as a viewer do with all this information? How should you engage with these unfolding mysteries? What should you be watching for? And why does getting this right matter? These are questions best reserved for future discussions. For now, thank you for joining me on this late-night journey into the depths of cosmic discovery. Sleep well and stay curious.